Hello there, and welcome to Science for Sleep, where we take a quiet look at the universe, follow the science wherever it leads, and hopefully allow the day to become a little less demanding while we do it. Tonight, we are leaving Earth behind, not in a hurry of course. There is no need to pack anything, check a departure board, or worry about whether your bag fits in the overhead compartment. We're simply going to imagine moving outward from our familiar little world and travelling about 49 light-years into space, toward a small red star that would be almost completely unremarkable if it were not for the extraordinary rocky planet circling very close beside it. That planet is called Kuaꞌkua. Astronomers also know it by the less memorable name LH S3844b, which sounds less like a distant world and more like something printed on the side of an electrical component. Kuaꞌkua is a much better name. It means butterfly in the Bribri language of Costa Rica, and it was officially adopted for the planet through an international naming program. Butterflies, of course, tend to bring to mind sunlight, gardens, leaves, and warm afternoons. The world carrying this name is rather different. Kuaꞌkua is a rocky planet larger than Earth, circling a small red dwarf star at an extremely close distance. It races around that star in a little over 11 hours, during the time it takes many of us to wake up, go through a normal day, have dinner, and begin wondering why we're still looking at our phones when we intended to sleep. Kuaꞌkua has completed an entire year, and its unusual calendar is only the beginning. As far as scientists can determine, Kuaꞌkua is very likely tidally locked to its star. That means the planet rotates at the same rate that it orbits. One side continually faces the star, while the opposite side continually faces away. There is no ordinary sunrise. There is no ordinary sunset. There is a hemisphere where the star remains in the sky, and another hemisphere where that star never appears at all. Imagine standing somewhere on Earth and watching the sun stop moving. Not for an afternoon, not because a cloud has hidden it, not because we have somehow forgotten how clocks work. Imagine the sun simply remaining in one part of the sky, day after day, year after year. Move to the other side of the planet, and the opposite happens. No dawn arrives. You could wait as long as you pleased. You could prepare breakfast, check the horizon, become impatient, prepare another breakfast, and repeat the process for several billion years. The star would still not rise. That is the basic situation we're going to explore tonight. A world divided between permanent day and permanent night. And before we travel any farther, perhaps take a moment to notice where you are right now. Where in the world are you listening from tonight? Is it daytime outside your window, or has the sun already gone down? Perhaps there are streetlights outside. Maybe there is rain against the glass. Maybe the room is completely dark apart from a phone screen, a bedside lamp, or whatever device is currently explaining exoplanets to you at an hour when more sensible people may already be asleep. And what time is it where you are? That question seems ordinary enough on Earth. We ask it constantly. We divide the planet into time zones, adjust clocks when we travel, argue twice a year about daylight saving time, and occasionally stare at an oven clock after a power cut, wondering whether anybody actually remembers how to set it. But on Kuaꞌkua, the familiar relationship between time and daylight becomes much stranger. A day would not be something marked by sunrise and sunset in the way we experience it. If you stood beneath the permanent dayside, the sky would not slowly darken at the end of the afternoon. There would be no evening approaching from the east. Shadows would not stretch because the star was sinking toward the horizon. The light would remain. On the permanent night side, darkness would not mean that morning was coming later. Morning would not be late. Morning simply would not be part of the local experience. There would still be time, obviously. Rocks could cool, surfaces could change. The planet would continue racing around its star. But the visual rhythm that has shaped life on Earth for billions of years would be absent. Here on our planet, light and darkness are so familiar that we usually do not think about how deeply they organise almost everything we do. We wake in the morning, we work during the day, we speak about evening as a transition, We use phrases such as tomorrow morning without stopping to appreciate that morning exists because Earth rotates. The sun appears to cross our sky because our planet is turning beneath it. Every roughly 24 hours, most places on Earth are carried through daylight and darkness again. It feels inevitable because it has always happened to us. But planets are not required to behave like Earth. The universe did not sign an agreement promising everybody a sunrise. Kuaꞌkua is a particularly clear reminder of that. It is close enough to its star and moves around it quickly enough that the gravitational relationship between the two has probably changed the planet's rotation over a very long time. Instead of spinning independently while orbiting, as Earth does, Kuaꞌkua appears to keep the same face toward its star. We already know this arrangement much closer to home. The Moon is tidally locked to Earth. That is why we always see roughly the same lunar hemisphere from the ground. The Moon does rotate, despite the common misunderstanding that it does not. It simply takes about the same amount of time to rotate once as it takes to orbit Earth once. If it did not rotate, we would eventually see every side of it as it travelled around us. Instead, its rotation and orbit remain synchronized. Kuaꞌkua seems to be doing something similar with its star. The difference is that the object facing it is not Earth. It is a star. So one hemisphere receives stellar energy continuously, while the other is permanently turned away. That raises an immediate question. What happens to a rocky planet when one side is heated without a nightly break, while the other side never receives direct starlight? On Earth, the atmosphere and oceans constantly redistribute energy. The equator receives more solar energy than the poles, but winds and ocean currents move enormous amounts of heat around the globe. Day turns into night before one side of Earth can simply continue heating forever. Weather systems carry warmth, moisture, and energy over great distances. Kuaꞌkua appears to have very little help of that kind. Observations have given astronomers strong reasons to think that it lacks a substantial atmosphere. More recent measurements with the James Webb Space Telescope have allowed researchers to investigate the thermal radiation coming from the planet itself and study its surface in far greater detail than would once have seemed possible for a rocky planet, almost 49 light-years away. That is worth pausing over for a moment. We cannot travel there. We cannot place a thermometer on the ground. No spacecraft has entered orbit around Kuaꞌkua. There is no lander sitting patiently on the surface sending photographs home. From Earth, the planet is not a little disk where we can point at mountains and craters. It's far too distant and far too small for that. And yet astronomers can separate clues hidden in light and begin asking what kind of surface exists there. The latest observations favour a dark, rocky surface, potentially rich in basalt or similar low silica material, without evidence that a thick atmosphere is covering it. In other words, Kuaꞌkua may be almost exactly the sort of place its strange day-night arrangement suggests. A bare world exposed directly to space, a hot dayside receiving energy from its nearby red star. A nightside with no sunlight and little atmosphere available to carry warmth across the planet. Between those extremes would be a region where the star sits low near the horizon. This boundary between the illuminated hemisphere and the dark hemisphere is called the terminator. On Earth, a terminator passes across the planet continuously. There is one moving boundary where morning arrives and another where evening begins. Viewed from space, Earth always has a dayside and nightside, but because Earth rotates, locations move through both. Right now, somewhere on Earth, people are watching sunrise. Elsewhere, someone is closing curtains because sunset has just arrived. Farther around the globe, people are asleep beneath the middle of the night. A few hours later, all of those locations will have moved into different lighting. Kuaꞌkua changes that picture. If the planet is locked as expected, the boundary stays in roughly the same place relative to the surface. There would be regions where the star remained low in the sky, instead of rising or setting in the usual sense. It is tempting to imagine that boundary as a comfortable middle ground. Perhaps one side is too hot, the other too cold, and somewhere between them everything becomes pleasantly mild, a sort of planetary porch. Unfortunately, Nature is usually less cooperative than the simple version of an idea. Temperature is not the only problem. A world needs more than a tolerable patch of ground to become friendly to life as we know it. Pressure matters, chemistry matters, water matters, radiation matters. Geological history matters. An atmosphere can matter enormously. Kuaꞌkua is useful precisely because it shows how many things can differ between two planets that are both made mainly of rock. Earth is rocky. Kuaꞌkua is rocky, and that is about where the resemblance stops being reassuring. Its star is very different from the Sun. Its orbit is astonishingly tight. Its year lasts a little over 11 hours. Its irradiation is far stronger than Earth's. Its rotation is probably locked. Its atmosphere, if anything remains at all, appears to be extremely thin compared with ours. Even the way we discovered it tells us something about the strange period of astronomy we are living through. For most of human history, the planets people knew were the wandering lights visible in our own sky. Mercury, Venus, Mars, Jupiter, and Saturn could be seen without telescopes. Uranus eventually joined the planetary list after telescopic observation. Neptune was predicted mathematically before being identified through a telescope. But planets around other stars remained ideas. People wondered whether they existed. Philosophers discussed them. Scientists suspected they might be common. For a very long time, there was simply no way to know. Now we have confirmed thousands of planets beyond the solar system, and the conversation has changed completely. The question is no longer simply whether other stars have worlds. They do. The more interesting question is what those worlds are actually like. Some orbit two stars, some are hotter than many stars, some are enormous gas giants skimming extremely close to their suns, others are small rocky planets orbiting cool red dwarfs, and a few are close enough, large enough, or positioned conveniently enough that our instruments can begin telling us something about their temperatures, atmospheres, and surfaces. Kuaꞌkua belongs to that last group. It was discovered through a transit, which occurs when a planet passes between us and its star, and blocks a small fraction of the star's light. Imagine looking at a distant lamp, while a tiny bead repeatedly crosses in front of it. If your instrument is sensitive enough, the lamp appears to dim by a very small amount each time the bead passes. Astronomers measure that dimming. From the pattern, they can determine the planet's orbital period. From the amount of light blocked, they can estimate the planet's size relative to the star. Repeat the observation enough times, combine it with what we know about the star itself, and a world that cannot be seen as a detailed object begins to acquire measurable properties. Kuaꞌkua is about 1.3 times Earth's radius. That makes it larger than our planet, but it's still very much in the rocky world category, rather than something like Neptune or Jupiter. Recent measurements of its mass also support the picture of a dense, predominantly rocky planet. So when we talk about a hot surface, a dark hemisphere, or a landscape exposed to space, we are not describing a gas giant where there may be no solid ground to stand on. There really is a rocky world there. Of course, standing on it would introduce several practical difficulties. The first would be arriving at all. 49 light-years sounds almost nearby by astronomical standards, and compared with the width of our galaxy, it is. But a light-year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second, or roughly 186,000 miles per second, and it still takes about 49 years to cross the distance between Kuaꞌkua's system and Earth. Our spacecraft do not travel remotely close to light speed, so this is not a destination for next year's holiday schedule. The lack of hotels is probably the smaller issue. Even if a convenient spacecraft somehow placed you on the planet, you would arrive in an environment unlike any ordinary place on Earth. The dayside is extremely hot. The star would appear redder than our Sun because Kuaꞌkua's host is a cool red dwarf, a type of small star that is much less massive and less luminous than the Sun. But less luminous does not mean gentle if you put a planet extremely close to it. A fireplace is less powerful than the Sun too, but this does not make sitting inside the fireplace an advisable way to warm up. Distance matters. Kuaꞌkua travels only a tiny fraction of the Earth-Sun distance from its star. That is why its year is measured in hours rather than months. Gravity keeps it moving rapidly around the star, completing orbit after orbit with remarkable speed. If you could watch the system from some comfortable location in space, the planet would seem almost frantic. The planet itself, however, would not experience its environment as a sequence of 11-hour days and nights. This is an important distinction. Its year is about 11 hours. Its solar day, under tidal locking, is effectively permanent. The same hemisphere continues facing inward. So there is no sunrise every 11 hours. There is no rapid alternation between scorching noon and freezing midnight. Instead, geography determines light. Where you are decides whether the star is overhead, near the horizon, or completely absent. That gives us a useful way to begin thinking about this world. Rather than asking what time of day it is on Kuaꞌkua, we might ask where on Kuaꞌkua we're talking about. At the point facing directly toward the star, the light would be strongest. Move away from that point, and the star would sit lower. Continue toward the boundary, and eventually it would approach the horizon. Cross far enough onto the opposite hemisphere, and the star would disappear. Stay there, and it would remain gone. No weather forecast would say sunrise at 6:42 tomorrow morning. There would be no tomorrow morning in that sense. Humans have never lived in such an environment, but the basic idea is not completely foreign to us. Near Earth's poles, daylight already behaves in ways that can surprise people accustomed to lower latitudes. During parts of the year, the sun may remain above the horizon for weeks or months. At other times, it can remain below it for equally long periods. People living in Arctic and Antarctic regions know that a neat 12-hour division between day and night is not a universal rule even here. But Earth's axial tilt and orbit eventually change the situation. The polar night ends, the midnight sun ends, the seasons move on. Kuaꞌkua takes the idea far beyond that. The star is not waiting below the horizon for the correct season. The permanent night is tied to the planet's orientation itself. There is something almost useful about such an extreme world, because extremes make physical processes easier to notice. If a planet has a thick atmosphere, winds can move heat from the hot side to the cold side. If it has oceans, currents can help. If it has neither, the contrast becomes much larger. That contrast is not merely something we imagine from theory. It is one of the clues astronomers can look for. As Kuaꞌkua moves around its star, we receive different proportions of thermal radiation from the hemisphere facing us. By measuring how the combined light of the star and planet changes during the orbit, scientists can build what is called a phase curve. It is a little like watching the phases of Venus or the Moon, except the planet is far too distant to see as a resolved crescent. Instead, astronomers measure changes in brightness. If a large amount of heat were being carried to the night side by a substantial atmosphere, the night hemisphere would radiate more energy than a bare, poorly connected surface would. The observations instead point toward a world where heat is not being redistributed very efficiently. The dayside gets hot. The night side remains much colder. That is one reason Kuaꞌkua became such an interesting target. It offers astronomers something they rarely get with rocky exoplanets, a chance to study the actual solid surface without a thick atmosphere hiding it. Normally an atmosphere is scientifically wonderful. It contains information about temperature, chemistry, weather, and potentially habitability. But if you are trying to understand the rock itself, an atmosphere can behave like a blanket covering the thing you want to inspect. Kuaꞌkua seems to have misplaced its blanket. That is unfortunate for Kuaꞌkua, assuming planets have opinions about blankets, but very useful for astronomers. The infrared light leaving its dayside carries information about the surface. Webb can collect that light. Scientists can compare the spectrum with laboratory measurements and models of different minerals and surface textures. From almost 49 light-years away, we can begin narrowing down what kind of rock may be exposed on another planet. Not an artistic guess. Not a science fiction painting. actual measurements of a real extrasolar surface. A generation ago, even detecting an Earth-sized planet around another star was a major achievement. Now, researchers are asking whether the exposed ground on one contains basalt, olivine-rich material, volcanic gases, or signs of weathering by space. That change in what astronomy can do is easy to overlook because discoveries arrive so quickly. Kuaꞌkwa gives us a reason to slow down and appreciate it. There is a small dark world moving around a red star. We know roughly how large it is. We know how quickly it completes an orbit. We can measure heat leaving its surface. We can test whether an atmosphere is moving that heat around. We can examine infrared wavelengths for clues about the rock, and with each measurement, the anonymous label LHS3844b becomes a place with physical conditions we can actually discuss. So as you settle in tonight, perhaps let your own familiar cycle of day and night continue outside without requiring any attention from you. Earth will keep rotating. Somewhere, dawn is arriving. Somewhere else, evening is beginning. Your local sky will change whether you stay awake for it or not. Kuaꞌkwa does not travel alone through the darkness. At the centre of its small system is the star known to astronomers as LHS 3844, and officially named Batsu, a Bribri word meaning hummingbird. The planet's name, Kuaꞌkwa, means butterfly. The names were adopted by the International Astronomical Union in 2023, giving a rather gentle pair of names to a system that is physically anything but gentle. A hummingbird and a butterfly sound as though they should belong in a warm garden somewhere. Instead, these two objects are separated by a distance so small, at least by planetary standards, that Kuaꞌkwa completes an entire orbit around its star in less than half an Earth day. Batsu is a red dwarf, one of the smallest and coolest kinds of ordinary stars in the universe. The word cool needs a little qualification here because astronomers have a slightly different relationship with temperature than most people. The surface of Batsu is around 3000 Kelvin, so standing anywhere near it would still be an exceptionally poor idea. It is called cool because the surface of our Sun is considerably hotter, roughly 5800 Kelvin. Compared with the Sun, Batsu is tiny. It has only around 15 or 16% of the Sun's mass, and its radius is less than 1/5 of the Sun's. If the Sun were somehow replaced by a red dwarf like Batsu, the object sitting at the centre of our solar system would suddenly look much smaller and much dimmer. It would also look different in colour. Our Sun emits strongly across visible wavelengths, and appears broadly white when viewed from space, although Earth's atmosphere often gives it a yellow, orange or red appearance, depending on where it is in the sky. A cool red dwarf produces a larger fraction of its energy at longer wavelengths, including red and infrared light. So if you could somehow stand on Kuaꞌkwa and look towards its star, ignoring for the moment the heat, radiation, lack of breathable air, and several other objections that a sensible travel agent might raise, you would not see anything resembling an ordinary sunny afternoon on Earth. The light would come from a smaller, cooler star. And because Kuaꞌkwa orbits so close to it, that small star would still dominate the planet's environment. This is one of the peculiar things about red dwarf systems. A star can be faint compared with the Sun, and still roast a planet if the planet sits close enough. We experience something similar in everyday life. A small heater on the opposite side of a room may feel pleasantly warm. Put your hand a few centimetres away from the same heater, and the size of the appliance suddenly becomes less important. Distance changes everything. Kuaꞌkwa orbits Batsu at only about 0.006 astronomical units. 1 astronomical unit is approximately the average distance between Earth and the Sun, about 150 million kilometres. Kuaꞌkwa's orbit is therefore measured in a tiny fraction of the distance that separates us from our star. The planet is packed tightly against Batsu, completing an orbit in roughly 0.463 Earth days. That closeness affects nearly everything about the world. It determines how much energy the surface receives. It helps explain why tidal forces are so important. It affects whether an atmosphere can survive, and it means that although Batsu is far less luminous than the Sun, Kuaꞌkua is still an intensely irradiated planet. Red dwarfs themselves are extremely important in the search for planets beyond our solar system because they are common, very common. The Milky Way contains far more low-mass red dwarfs than stars like the Sun. They are modest stars. They burn their fuel slowly. They can survive for enormously long periods of time, much longer than the roughly 10 billion year main sequence lifetime expected for a star like our Sun. From the point of view of a planet looking for long-term stability, that sounds promising. A red dwarf is not in a hurry. The difficulty is that small stars come with their own complications. Because they produce less light, a planet must orbit much closer to receive the same general amount of energy that Earth receives from the Sun. Bring a planet inward, and gravity begins to alter the situation. Tidal forces become stronger, orbital periods become shorter, stellar radiation becomes more concentrated. Activity from the star can become increasingly important. This is why red dwarf planets are so interesting. They may be among the most common rocky worlds in the galaxy, yet they live under conditions very different from those that shaped Earth. Batsu is an M5 dwarf, a relatively late type of M dwarf. Current estimates put it around 15 parsecs from us, or approximately 49 light-years away. A 2026 analysis described it as an old, slowly rotating star, with an estimated age of roughly 7.8 billion years and a rotation period around 130 days. That makes the system older than our solar system, which formed about 4.6 billion years ago. So Kuaꞌkua is not a newborn world circling a young star. Whatever has happened to its surface has had plenty of time to happen. Whatever atmosphere it may once have possessed has spent billions of years dealing with its surroundings. Whatever volcanic activity shaped its visible surface may also have slowed or changed long ago. And Batsu itself has had time to settle into its current relatively quiet state. That word relatively matters. Red dwarfs are famous for stellar activity, particularly when they are young. They can produce flares and strong ultraviolet and X-ray radiation. A flare on a red dwarf can increase the amount of high-energy radiation reaching a nearby planet, sometimes dramatically. For a world orbiting far away, this might be interesting. For a world sitting extremely close to the star, it can become part of the planet's long-term geological and atmospheric history. Astronomers have studied the ultraviolet environment of Batsu directly. Observations with the Hubble Space Telescope detected a far ultraviolet flare, while measurements of the star outside the flare showed that it is relatively inactive compared with the more violent examples of its class. Researchers study this high-energy output because it helps reconstruct the radiation environment experienced by Kuaꞌkua and similar rocky planets. The planet we see today may therefore be partly the product of billions of years spent close to a red dwarf. Imagine a young rocky planet shortly after formation. Its interior is hot. Volcanoes release gases. Impacts rearrange the surface. Depending on how the planet formed, it may begin with an atmosphere or build one through volcanic outgassing. On Earth, gases released from the interior became part of a long and complicated story involving oceans, rocks, chemistry, biology, and the gradual evolution of the atmosphere above us. Kuaꞌkua had a very different address. Being extremely close to Batsu means the planet receives intense stellar energy. High-energy radiation can heat the upper layers of an atmosphere. Energetic particles carried in a stellar wind can interact with atmospheric gases. Over long periods, atoms and molecules may escape into space. A planet's gravity tries to hold its atmosphere down. The star's environment helps pull it away. Which side wins depends on many things: the planet's mass, temperature, atmospheric composition, magnetic environment, volcanic replenishment, stellar activity, and the amount of time available. Kuaꞌkua has had plenty of time. In 2019, observations with the Spitzer Space Telescope gave scientists an important clue. They measured thermal radiation from the planet over its orbit and found a very large difference between the hot hemisphere and the dark hemisphere. The dayside brightness temperature was around 1040 Kelvin at the wavelength observed, while the nightside signal was consistent with essentially no detectable thermal emission in that measurement. A thick atmosphere would tend to transport heat from the illuminated side toward the dark side, reducing that enormous contrast. The data instead fitted a bare, dark, rocky surface rather well. That does not mean the night side is literally at absolute zero. It means Spitzer did not detect enough heat from it to require a warm night side in the model. The important point was the contrast. A substantial atmosphere behaves like a planetary delivery service. Sunlight warms one region, air moves, winds carry energy elsewhere, pressure systems form, heat is redistributed. Earth does this constantly. Warm air moves away from the tropics. Cold air moves toward lower latitudes. Ocean currents transport energy across enormous distances. Weather, for all the inconvenience it creates when you forget an umbrella, is part of a planet-wide heat distribution system. Kuaꞌkua appears to lack that kind of efficient atmospheric circulation. The star heats the dayside. The night side receives little of that energy. The surface itself must deal with the difference. Recent observations have strengthened this picture. In 2026, researchers reported a thermal emission spectrum of Kuaꞌkua obtained with the James Webb Space Telescope. The spectrum was best matched by a dark, low-silica rocky surface, including possibilities such as basalt or olivine-rich material. The observations also placed tight limits on carbon dioxide and sulfur dioxide above the surface, and found no evidence for an accumulated atmosphere of volcanic gases. So when we imagine Kuaꞌkua beneath its red dwarf, it is useful not to imagine a smaller version of Earth under a different coloured sun. There may be no blue sky. There may be no clouds. There may be no wind moving dust across the ground. There may be no sound carried through open air. If the surface is essentially airless, looking upward would resemble looking into space from the moon, more than looking upward from Earth. The star would shine in a dark sky. Stars might remain visible around it depending on the glare and where you were looking. There would be no blue atmospheric scattering filling the sky with daylight. On Earth, the sky's blue because molecules in our atmosphere scatter shorter visible wavelengths more strongly than longer ones. Remove the atmosphere and the blue dome disappears. Apollo astronauts stood on the moon in full sunlight beneath a black sky. Kuaꞌkua's permanent dayside may offer the same basic visual contradiction on a much hotter world, brilliant direct stellar illumination falling across rock while the sky above remains dark. The star itself would also behave strangely from the surface. Because Kuaꞌkua is expected to be tidally locked, Batsu would not cross the sky every day. At the location directly facing the star, known as the substellar point, Batsu would remain roughly overhead. Walk away from that location and the star would appear lower. Continue toward the boundary between permanent illumination and permanent darkness, and it would approach the horizon. There is no normal afternoon because the star does not gradually sink. There is no evening arriving because the planet has turned away. The local lighting is determined mainly by location rather than time of day. That would change the meaning of almost every ordinary expression humans use about daylight. You could not wait for noon. You could not get up before sunrise. You could not watch the sunset after dinner. There would be no reason to say that the days are getting shorter. On much of Kuaꞌkua, the day has stopped changing altogether. This does not mean the planet is frozen in space. Quite the opposite. Kuaꞌkua is moving extremely quickly around Batsu. Its orbital period is less than 11 hours and 7 minutes. While you are sleeping through a normal 8-hour night on Earth, Kuaꞌkua would travel most of the way around its star. During one Earth week, it would complete more than 15 orbits. In one Earth year, hundreds. Yet from the surface, assuming tidal locking, the star would remain in roughly the same direction. The planet moves around the star while rotating once during each orbit, continuously turning just enough to keep the same hemisphere pointed inward. It is a lovely piece of orbital geometry, although probably less lovely if you happen to be the rock sitting beneath the hottest part of it. Tidal locking is not unusual. Our moon is locked to Earth. Many moons throughout the solar system are locked to their planets. When two bodies orbit close together, gravity pulls more strongly on the near side than on the far side. Over time, those unequal forces create tidal effects that can change rotation. Energy is dissipated, and the smaller body's spin can gradually settle into a synchronized state. For Kuaꞌkwa, with its extremely tight orbit, tidal forces are expected to have acted strongly. This gives the world two very different environments separated not by seasons or time zones, but by longitude. Near the middle of the dayside, the surface receives intense energy continually. Dark rock absorbs much of that radiation. There is no atmospheric cloud deck to reflect a large fraction back into space, as far as observations currently suggest. There is no ordinary night to interrupt the heating. The surface reaches very high temperatures and radiates energy away in infrared wavelengths. Move toward the edge of the illuminated hemisphere, and the angle of incoming light decreases. The same stellar energy is spread over a larger area of ground. Temperatures should fall, then the star reaches the horizon. Beyond that line, direct stellar heating disappears. The ground must rely on heat conducted through the rock, internal geothermal energy, and whatever limited energy may reach it through other processes. Without a thick atmosphere transporting warmth, the night side can become dramatically colder than the day side. So although people sometimes describe tidally locked planets as having a permanent day and permanent night, those words conceal an entire range of conditions. The day side itself is not one uniform temperature. The night side is not necessarily one uniform temperature. The boundary region is not a narrow magical strip with one convenient climate. Real planetary surfaces have elevation differences, different minerals, different thermal properties, shadows, craters, perhaps ancient volcanic plains, and variations in how efficiently the ground absorbs and releases heat. Kuaꞌkwa may be dark overall, but dark rock can make the contrast with its star even more important. A low albedo means the surface reflects relatively little incoming energy. Spitzer's earlier results were consistent with a bond albedo below about 0.2, meaning the planet absorbs most of the stellar energy reaching it rather than reflecting it away. The 2026 Webb spectrum likewise points toward a dark surface and favours low silica material, such as basalt or olivine-rich rock. Basalt is familiar to us. Much of Earth's oceanic crust is basaltic. Large areas of the Moon are covered by basaltic plains formed by ancient lava flows. Mars has extensive basaltic material. Volcanic islands on Earth frequently begin with basaltic lava rising from the mantle. So the suggestion that Kuaꞌkwa may have a basalt-like surface does not require an exotic new kind of rock. The exotic part is the environment in which that rock now sits. Imagine something chemically related to familiar volcanic stone, but exposed for immense periods beneath a red dwarf, heated on one hemisphere, left in darkness on the other, without rain or rivers constantly breaking it down, and apparently without a thick atmosphere protecting it from the space environment. A bare surface ages differently from one beneath air and water. On Earth, wind moves particles. Rain dissolves minerals. Rivers grind rock into sediment. Oxygen reacts with iron. Plants break into cracks. Freeze-thaw cycles split stone apart. Plate tectonics recycle large portions of the crust. Our landscape is constantly being altered by a planet that refuses to leave its rocks alone. On an airless world, different processes dominate. Micrometeorites strike the ground. High-energy particles affect exposed minerals. Radiation changes materials at the surface. Impacts break rock into smaller fragments. Over long periods, these processes create what scientists broadly call space weathering. The 2026 Webb analysis found that Kuaꞌkwa's spectrum is consistent with an old, space-weathered surface. Fresh fine powders were not a good match by themselves, although weathering that darkened surface material could make such textures more compatible with the observations. It is an extraordinary amount of information to extract from a planet that we cannot see as a landscape. No telescope has photographed a Kuaꞌkwa mountain. We do not have a map of its craters. There is no image of Batsu hanging over a black horizon. What we have are tiny changes in light, a slight dimming when the planet passes in front of its star, a change in infrared brightness as different portions of the heated surface face us, a disappearance of the planet's own thermal contribution when it passes behind the star, a spectrum carrying subtle information about how the surface emits radiation at different wavelengths. From those measurements, a physical world emerges. Its radius is about 1.29 times Earth's according to recent estimates. Two independent 2026 radial velocity analyses measured its mass at a little over twice Earth's, supporting a predominantly rocky composition, rather than a low-density planet wrapped in a massive gas envelope. One analysis found about 2.27 Earth masses, another found about 2.37. The exact numbers differ slightly because the teams use different observations and modelling approaches, but the broad result agrees. Kuaꞌkwa is a dense terrestrial world. So beneath Batsu, there is not merely a point on an astronomer's graph. There is enough rock to build a planet larger than Earth. There is gravity. There is a surface receiving and releasing heat. There is a long history written into dark minerals. There may once have been gases above it that are no longer there. There may have been periods of volcanic activity that altered broad areas of the surface, and all of it has developed beside a star that is smaller, redder, cooler, and far longer lived than our Sun. The contrast with Earth is useful because red dwarfs may host an enormous fraction of the rocky planets in our galaxy. If we want to know what rocky planets normally look like, studying only worlds around Sun-like stars would give us a very incomplete answer. Our own planetary system may represent only one way for rocky worlds to grow up. Around red dwarfs, planets commonly orbit much closer. Their skies receive different stellar spectra. Their rotation can become synchronized. Their atmospheres face different pressures from stellar radiation. Their climates, when atmospheres exist, can settle into patterns unlike anything familiar from Earth's daily rhythm. Kuaꞌkwa happens to offer an extreme case. It sits much closer to its star than a habitable zone planet would. The amount of energy it receives makes liquid surface water extraordinarily unlikely under the conditions we observe today. Its apparent lack of a substantial atmosphere makes the environment even harsher. But that is exactly why astronomers care about it. To understand which rocky planets can hold atmospheres, it helps to find one that apparently could not. To understand how stellar radiation changes planetary surfaces, it helps to examine exposed rock. To understand tidally locked worlds, it helps to study a planet where heat seems to remain strongly concentrated on the illuminated hemisphere. Kuaꞌkwa becomes a kind of natural laboratory. The experiment has already been running for billions of years. We simply arrived recently enough to start reading the results, and Batsu is part of the experiment. The star is not merely a lamp hanging above the landscape. Its gravity controls the orbit. Its radiation heats the rock. Its high energy output influences atmospheric escape. Its long life provides the timescale across which all these processes unfold. Planet and star have spent their history interacting. That relationship is easy to miss when we speak about exoplanets individually. A planet is never just a planet. Its star determines the amount and type of radiation arriving at the surface. Its orbit sets the rhythm of heating. Its neighbours, if any exist, can disturb that orbit. Its own mass and composition decide how it responds. In the case of Kuaꞌkwa, the relationship is especially intimate because the planet circles so close to Batsu that the distance between them seems almost uncomfortable by solar system standards. That remarkably short orbit is where the geometry of Kuaꞌkwa begins to become genuinely difficult to picture, because an 11-hour year is not simply a shorter version of the year we experience on Earth. It means the entire scale of the planetary system has been compressed. The star is closer, the planet is moving faster, and processes that take months or years in our solar system can happen before an ordinary working day on Earth is finished. Kuaꞌkua completes one orbit around Batsu in about 0.46293 Earth days. That works out to a little over 11 hours. By comparison, Earth needs about 365.25 days to travel once around the Sun. Mercury, the fastest planet in our solar system, still takes about 88 Earth days. Even Mercury, which seems to race around the Sun when compared with Earth, would look rather relaxed beside Kuaꞌkua. Suppose an observer on Earth began following Kuaꞌkua at 7 in the morning. Before lunchtime, the planet would already have covered a large portion of its orbit. By early evening, it would be approaching the place where it began. Before the observer went to bed, Kuaꞌkua would have completed an entire year and started another. If your birthday were measured using Kuaꞌkua years, the celebrations would become impractical almost immediately. A person who had lived for 30 Earth years would have experienced well over 23,000 Kuaꞌkua years. Candles would become a serious logistical problem, and nobody would have time to write the cards. This short period exists because Kuaꞌkua orbits extremely close to Batsu. Its average orbital distance is only about 0.0062 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun, so Kuaꞌkua sits at less than 1% of the Earth-Sun distance from its own star. That number can sound rather meaningless until we turn it into something more familiar. Earth is about 150 million kilometers from the Sun on average. Kuaꞌkua is only around 930,000 kilometers from Batsu. That is still a large distance by everyday standards. You could fit the Earth-Moon distance into it more than twice, but for a planet orbiting a star, it is astonishingly close. Mercury never comes remotely that close to the Sun. Kuaꞌkua is not sitting at the comfortable outer edge of a quiet planetary system. It is tucked close beside its red dwarf, held in a tight orbit by gravity, and moving rapidly enough to circle the star twice during a single Earth day, with time left over. There is a simple reason planets move faster when they orbit closer to a star. Gravity becomes stronger as the distance decreases. A planet farther away can travel more slowly and still remain in orbit. A planet very close to its star must move rapidly enough that, as gravity continually pulls it inward, its sideways motion keeps carrying it around the star, rather than allowing it to fall directly toward it. Orbiting is, in a sense, a very well-organized form of falling. Earth is falling toward the Sun all the time. Fortunately, we're also moving sideways at nearly 30 kilometers per second, so we continuously miss. This has been going on for about 4.6 billion years, which suggests that missing the Sun can be quite a stable arrangement if you do it properly. Kuaꞌkua follows the same basic principle, but its orbital motion is much faster. Using its measured orbital distance and period, the planet's average orbital speed works out to roughly 145 kilometers per second. That is close to 500,000 kilometers per hour. At that speed, a trip around Earth's equator would take only a few minutes, although taking a rocky exoplanet through Earth's atmosphere at 145 kilometers per second would introduce several additional complications. The reason Kuaꞌkua remains in such a stable, tight path is that Batsu is much less massive than the Sun. It has only around 15% of the Sun's mass, so although the planet is extremely close, it is not orbiting something with the gravitational strength of our Sun. This combination, a low-mass star and a very close planet, produces the short 11-hour period. Johannes Kepler would have recognized the pattern. More than 4 centuries ago, Kepler described how planets move around the Sun and showed that their orbital periods are closely connected to their distance from the object they orbit. Planets close to the Sun complete their journeys quickly. Planets farther away move through much longer years. Mercury takes 88 days, Venus takes 225, Earth takes 365, Mars requires 687, Jupiter takes nearly 12 Earth years, Neptune needs almost 165. If you arrange the solar system from the inside outward, the years grow longer and longer. Kuaꞌkua simply pushes that familiar relationship into a range we do not have in our own planetary neighbourhood. Its orbit is so compact that the idea of a planetary year becomes disconnected from our everyday feeling of what a year should be. On Earth, A year is long enough to contain seasons. People grow older. Children move through school years. Trees change. Animals migrate. Holidays return. We remember what happened last year because enough time has passed for the phrase to carry some weight. None of that is built into the physical definition of a year. A year is simply the time required for a planet to complete an orbit. The universe has no requirement that it last long enough to organise a calendar. For Neptune, a year lasts longer than a human lifetime. For Kuaꞌkua, it lasts less than half a day. Both are perfectly valid planetary years. Our sense that 365 days feels natural comes from the fact that we were born on the one planet where 365 days happens to be normal. If humanity had evolved on a world with a 10-day orbit, perhaps the word year would feel like something much smaller. If we had evolved on Neptune, nobody would have an annual birthday in the usual sense, because most people would not reach their first one. The calendar would need some adjustment. Kuaꞌkua takes that idea to an extreme. Its orbital period is classified as ultra-short. Astronomers commonly use the term ultra-short period planet for worlds whose years are shorter than about one Earth day. Kuaꞌkua falls comfortably into that category, or perhaps uncomfortably, depending on how one feels about living next to a star. These planets are especially interesting because their very existence raises questions. How did they get there? Did they form so close to their stars? Did they begin farther away and migrate inward? What happens to rock, atmosphere and planetary interiors after billions of years in such tight orbits? The region around a young star is a complicated place. Planets form from disks of gas and dust surrounding young stars. Small solid grains collide and stick together. Larger bodies develop. Those bodies collide again. Over time, some become planets. But planets do not necessarily remain exactly where they formed. They can exchange angular momentum with the material in the disk. They can gravitationally interact with other planets. Orbits can shift. Some planets migrate inward. Others move outward. Some are thrown into eccentric paths. A few may even be expelled entirely, left wandering between stars with no sunrise at all. So when astronomers find a rocky world pressed very close to a star, they naturally wonder whether it was born there or arrived there later. Kuaꞌkua does not provide an easy answer. Its present orbit tells us where it is now, but not every detail of how it arrived. One possibility is that material close to Batsu assembled into rocky planets early in the system's history. Another is that Kuaꞌkua formed farther away and migrated inward while the system was young. Gravitational interactions might also have changed its orbit before tidal forces gradually settled it into the compact, nearly circular path we observe today. Whatever sequence occurred, the result is a planet that has spent a very long time close to its star. Recent research estimates Batsu to be billions of years old, which means the 11-hour orbit is not a temporary situation we happen to be witnessing during some brief early stage. Kuaꞌkua is an old planet in an old system. Its current environment has likely shaped it over immense spans of time. That tight orbit affects more than the length of its year. It also exposes Kuaꞌkua to a tremendous amount of stellar energy. The NASA Exoplanet Archive lists an incident stellar flux of roughly 70 times what Earth receives from the Sun, depending on the adopted stellar and planetary parameters. Again, Batsu is much dimmer than the Sun. The reason Kuaꞌkua receives so much energy is simply that it sits so close. Moving closer to a source of radiation has a dramatic effect, because the same energy becomes concentrated over a smaller area. If you double your distance from a light source, the amount of energy received per unit area drops sharply. Move inward, and it rises just as quickly. Kuaꞌkua has moved, whether through formation or migration, into a region where a faint red dwarf is no longer faint from the planet's point of view. The result is a surface that becomes extremely hot on the hemisphere facing the star. Earlier, Spitzer observations measured a dayside brightness temperature of around 1040 Kelvin at 4.5 micrometers. That is roughly 770 degrees Celsius, although a brightness temperature at one infrared wavelength is not exactly the same thing as saying every point on the surface has that temperature. The important result was that the dayside was intensely hot, while the nightside showed very little detectable thermal emission, pointing toward inefficient heat redistribution and the absence of a thick atmosphere. There is another useful consequence of an 11-hour orbit, at least for astronomers sitting comfortably 49 light-years away. Kuaꞌkwa repeats itself often. A transiting planet passes between us and its star once per orbit. If a planet takes 12 years to orbit, you may need a great deal of patience to watch several transits. Kuaꞌkwa offers a new transit roughly every 11 hours. That repetition makes it easier to gather many observations and improve measurements of the orbital period. The transit itself lasts only about half an hour. During that short interval, Kuaꞌkwa moves across the face of Batsu as seen from Earth and blocks a small fraction of the star's light. The star becomes slightly dimmer, then the planet moves away and the brightness returns. Nothing about this is visually dramatic through an ordinary telescope. There is no tiny black planet that we can watch crossing a giant red disk from a backyard observatory. The system is much too distant for that. Instead, sensitive instruments measure the star's light and detect the regular decrease. A dip occurs. 11 hours later, another dip occurs, then another. Soon a pattern becomes difficult to ignore. This regularity is how a planet that cannot be seen as a resolved globe can reveal the length of its year with remarkable precision. The measured period is known to far more precision than simply saying 11 hours. Current values are around 0.4629296 days, with uncertainties measured in tiny fractions of a day. That precision may seem slightly excessive. After all, nobody is planning to catch the 6:15 orbital departure from Kuaꞌkwa Central Station. But precise orbital timing becomes important when astronomers combine observations taken years apart. If the period were even slightly wrong, predictions of future transits would gradually drift. A tiny error repeated across thousands of orbits eventually becomes a large timing error. Kuaꞌkwa has completed roughly 800 orbits during a single Earth year. Over several Earth years that becomes thousands. So scientists need very accurate orbital measurements to know where the planet should be at a particular moment. Repeated transits can also reveal whether something is disturbing the orbit. If another planet pulls gravitationally on Kuaꞌkwa, its transits might occur slightly early or late. Astronomers can search for these transit timing variations as clues to other bodies in the system. The orbit also helps us measure the planet in other ways. As Kuaꞌkwa moves around Batsu, the planet's gravity pulls slightly on the star. We usually say that a planet orbits its star, which is a perfectly good description for everyday purposes, but technically both objects orbit their common centre of mass. Because Batsu is vastly more massive, its motion is tiny. Kuaꞌkwa travels around the system in a wide little circle, while Batsu performs a much smaller wobble. Astronomers can detect that wobble by measuring changes in the star's spectrum. When Batsu moves slightly toward Earth, its spectral lines shift toward shorter wavelengths. When it moves away, they shift toward longer wavelengths. This is the radial velocity method, and the same 11-hour period appears there too. The star is being pulled toward us, away from us, toward us, away from us, following the rapid rhythm of its close companion. In 2026, independent radial velocity studies reported measurements, putting Kuaꞌkwa's mass a little above twice Earth's mass. One analysis found about 2.27 Earth masses, while another found about 2.37. Combined with the measured radius, those results reinforce the conclusion that Kuaꞌkwa is a dense rocky planet rather than a small gaseous one. The orbital speed and closeness also mean that conditions are very different from those on Earth, even before we consider the permanent day and night. Earth's orbit is only mildly eccentric, so our distance from the Sun changes by a modest amount throughout the year. Kuaꞌkwa's orbit is generally modelled as essentially circular. That makes sense for a very close planet. tidal effects tend to reduce orbital eccentricity over time, turning a stretched ellipse into a more circular path. A highly eccentric orbit would cause the star-planet distance to change significantly during each 11-hour year. The planet would receive more energy near the close part of the orbit and less farther away. Instead, the current picture is one of a world circling at nearly the same distance again and again. That matters because the intense stellar heating does not switch on only during a brief close approach. Kuaꞌkwa lives there permanently. Every orbit returns it to the same geometry. Every 11 hours it has gone around again without receiving any meaningful holiday from the star. There is also no long winter when the planet moves into some distant part of its orbit. Earth's seasons are not caused mainly by orbital distance, of course. They come from the tilt of Earth's rotational axis, but our idea of a year is still closely connected to a changing seasonal cycle. Kuaꞌkwa is unlikely to have seasons resembling ours. Its close orbit, tidal evolution, and probable locked rotation create a much simpler but more extreme pattern. The star-facing side remains heavily irradiated. The opposite side remains deprived of direct starlight. Instead of spring, summer, autumn and winter moving across a calendar, the major environmental difference is written onto the planet's geography. It would be tempting to think that the 11-hour year means the star must race across the Kuaꞌkwan sky. That would be true if the planet were rotating independently in a way that produced ordinary sunrises and sunsets. But this is where orbital motion begins to produce the strangest result of all. A planet can travel rapidly around a star without the star appearing to move rapidly through its sky. The Moon gives us the easiest way to understand why. The Moon orbits Earth once in about 27.3 days relative to distant stars. During that same period, it rotates once on its axis. Those two motions stay synchronized. As a result, the same side of the Moon remains pointed approximately toward Earth. Imagine drawing a face on the near side of the Moon. As the Moon travels around Earth, the face keeps looking inward. For that to happen, the Moon has to rotate. After 1/4 of its orbit, it is turned by roughly 1/4 of a rotation. Halfway around, it has rotated about halfway. By the time it completes the orbit, it has also completed one full turn. The same principle applies to Kuaꞌkwa if it is synchronously rotating, as observations and tidal theory indicate. It completes an orbit in about 11 hours. It also rotates once in about 11 hours. To an observer watching from far above the system, Kuaꞌkwa is spinning rapidly. To someone standing at one fixed point on the planet, Batsu can remain almost stationary in the sky. That sounds contradictory only because we are accustomed to Earth. Here, rotation makes the sun move across the sky. On a synchronized world, rotation is exactly what prevents the star from moving across the sky. Consider the point on Kuaꞌkwa facing directly toward Batsu. As the planet moves 1/4 of the way through its orbit, that point would begin turning away from the star unless the planet rotated. But Kuaꞌkwa also turns by 1/4 of a rotation. The point remains facing Batsu. Another quarter orbit passes. Another quarter turn occurs. The star stays in roughly the same place. The process repeats continuously. An 11-hour year therefore does not mean an 11-hour day-night cycle. Quite the opposite. The rapid year is closely connected to the reason there may be no ordinary day-night cycle at all. This is one of those places where astronomical language becomes slightly dangerous because the word day can mean several different things. There is the time required for a planet to rotate once relative to distant stars, sometimes called a sidereal day. Then there is the solar day, the interval between one local noon and the next. On Earth, those values are close but not identical. Earth rotates once relative to the stars in about 23 hours and 56 minutes, while our average solar day is 24 hours, because Earth has moved along its orbit during that rotation and must turn slightly farther for the Sun to return to the same position in the sky. On a synchronously rotating planet, the situation becomes much stranger. Kuaꞌkwa may rotate relative to distant stars every 11 hours or so, yet the same hemisphere continues pointing toward Batsu. Its rotation and orbital motion cancel each other from the star's apparent position. There is no next noon in the ordinary sense because noon never leaves the substellar point. There is no sunrise waiting to follow the night because the night side does not rotate into the light. The 11-hour year produces motion on a scale that is almost frantic when viewed from outside, while the local sky may appear almost fixed. That contrast is important. Kuaꞌkua is not a planet that simply forgot to rotate. It rotates very quickly. It has to rotate quickly in order to keep the same side facing its star while completing such a rapid orbit. This is why saying that a tidally locked planet does not rotate is incorrect. If Kuaꞌkua truly did not rotate relative to distant space, every part of its surface would face Batsu during one part of the orbit and turn away during another. It would experience a stellar day lasting about one orbit. Permanent day and permanent night require rotation. They simply require rotation synchronized with orbital motion. The source of that synchronization is gravity. When two bodies are close enough for long enough, the difference in gravitational pull across one of them can gradually alter its spin. The side closer to the star feels a slightly stronger pull than the side farther away. The planet is not a perfect rigid sphere, so these forces create tidal distortions. If the planet's rotation does not match its orbit, the tidal bulge is carried slightly out of alignment. The star's gravity pulls on that bulge and produces a torque. Over immense stretches of time, rotational energy is dissipated, and the spin can settle into a stable relationship with the orbit. Kuaꞌkua has almost every condition needed for this process to be powerful. It is extremely close to Batsu. The system is old. Its orbit is short. The tidal interaction has had billions of years to act. A 2024 study specifically investigating Kuaꞌkua's rotation found evidence favouring a tidally locked state, and the 2026 Webb surface analysis likewise treats synchronous rotation as part of the current physical picture of the planet. The 11-hour orbit, then, is not just a curious fact to put beside the planet's name. It explains why Kuaꞌkua is so hot. It tells us how close it is to Batsu. It gives astronomers frequent transits. The 11-hour orbit gives Kuaꞌkua an unusually short year, but it also creates something much more important than a difficult calendar. At such a small distance from Batsu, gravity has had billions of years to influence the way the planet rotates. The result appears to be synchronous rotation, more commonly described as tidal locking. This is the arrangement responsible for Kuaꞌkua's permanent day and permanent night. It is also one of those astronomical ideas that sound simple until we try to picture what is actually moving. A tidally locked planet is often described as keeping one side permanently facing its star. That is correct. What is not correct is the common idea that such a planet has stopped rotating. Kuaꞌkua rotates. In fact, it rotates very quickly. It simply completes one rotation in the same amount of time that it takes to complete one orbit around Batsu. Since the orbit lasts roughly 11 hours, the rotation also lasts roughly 11 hours relative to distant space. The two motions remain synchronized. If the planet did not rotate at all, every part of its surface would eventually face the star as it moved around its orbit. You can demonstrate this with almost anything nearby. Imagine a table lamp representing Batsu. Take a mug and let one side of the mug represent a particular location on Kuaꞌkua. Now carry the mug in a circle around the lamp, while keeping the mug pointed in exactly the same direction relative to the room. At the beginning, the handle might face the lamp. After half an orbit, the handle faces away from the lamp. Complete the circle and the handle returns to the illuminated side. The mug did not rotate relative to the room, but every side of it experienced light and darkness. Now repeat the orbit while slowly turning the mug so that the handle always faces the lamp. After one complete orbit, the mug has also completed one full rotation. The handle has remained pointed toward the lamp the entire time. That is synchronous rotation. The moon does the same thing with Earth. We see approximately the same lunar hemisphere every night because the moon takes about the same amount of time to rotate once as it takes to travel once around Earth. The far side is not permanently dark, despite the phrase "dark side of the moon" having survived remarkably well in popular culture. The far side receives sunlight just as the near side does. It is simply the side that usually faces away from Earth. Kuaꞌkua is different because it is locked directly to a star. The hemisphere facing Batsu receives starlight continuously. The opposite hemisphere receives no direct starlight. That distinction turns an ordinary orbital synchronization into an extreme environmental condition. The reason tidal locking occurs begins with something we already experience on Earth: tides. The moon's gravity pulls on our planet. Because the side of Earth facing the moon is slightly closer to it than Earth's centre, the gravitational pull there is slightly stronger. The far side is slightly farther away and feels a slightly weaker pull. That difference stretches Earth a little. Our oceans make the effect easy to notice, but tides are not limited to water. Solid rock also deforms under gravitational forces. Earth itself changes shape slightly as the moon and sun pull on it. The word tide in tidal locking refers to this difference in gravitational attraction across an object. Kuaꞌkua is so close to Batsu that the difference between the stellar pull on its near side and far side is significant. The planet is rocky and appears solid, but solid does not mean perfectly rigid. Rock can deform. The effect may be tiny at any particular moment, but if gravity continuously pulls on a planet for millions or billions of years, tiny deformations can influence its rotation. Suppose a young Kuaꞌkua once rotated faster than it does today. Perhaps the star rose and set across the surface. Perhaps a location experienced a rapid sequence of day and night while the young planet raced around Batsu. As the star's gravity raised a tidal distortion in the planet, that distortion would not necessarily point perfectly toward Batsu. A rotating planet carries the distorted region slightly away from the direct star-planet line. Batsu's gravity then pulls on that misaligned bulge. That produces a torque. A torque is simply a force that changes rotation. Push on a door near the hinges and very little happens. Push near the handle and the door rotates easily. The same basic principle applies on a much larger scale when gravity pulls unevenly on an extended object. The torque created by the star can gradually change the planet's spin. Energy associated with the original rotation is dissipated inside the planet, partly as heat caused by repeated deformation. The spin slows. Eventually the planet can settle into a state where one rotation matches one orbit. Once that happens, the tidal deformation no longer has to be carried rapidly out of alignment by the planet's rotation. The same hemisphere remains facing the star. For a planet with Kuaꞌkua's very tight orbit, synchronous rotation is exactly the kind of state tidal theory leads us to expect. But expectation is not the same as observation. For years, astronomers routinely assumed that many close-in rocky exoplanets were tidally locked, because the physics made the outcome highly likely. Actually demonstrating that one of those distant planets was rotating synchronously was much harder. Kuaꞌkua became particularly useful because it appears to have little or no substantial atmosphere. That may sound like a disadvantage, and from the planet's point of view it probably is. For astronomers trying to measure rotation, however, the lack of a thick atmosphere removes an important complication. An atmosphere can move heat. If one hemisphere receives constant stellar energy, winds can carry some of that energy toward the night side. A thick enough atmosphere can make a cold, dark hemisphere warmer and can shift the hottest region of a planet away from the point directly beneath the star. The planet's thermal glow then reflects both its rotation and its atmospheric circulation. Kuaꞌkua seems much simpler. Spitzer observations showed a very strong thermal contrast between its illuminated and dark hemispheres, with a dayside brightness temperature near 1040 Kelvin and no significant nightside thermal signal in that measurement. The large contrast was consistent with a bare rocky planet and ruled out thick atmospheres above roughly 10 bars in the models considered by the original study. That gave researchers a rare opportunity. If the surface is exposed and the planet rotates differently from synchronous rotation, the pattern of heating across the ground should change. Rock does not instantly jump to a new temperature whenever light reaches it. It takes time to heat and time to cool. Different materials store and conduct heat differently, but all surfaces have some thermal inertia. You know this from walking outside after sunset. A road or stone wall can remain warm after the sun has disappeared because it's stored energy during the day. Sand may cool more quickly. Water responds more slowly. The temperature of a surface therefore contains information about its recent exposure to radiation. On Kuaꞌkua, that becomes a way to test rotation. Imagine that the planet were not tidally locked. The star would move across the local sky. A patch of ground would heat when it rotated into daylight and cool when it rotated into darkness. The hottest point on the surface would not necessarily remain exactly where a simple, synchronized model predicts. The planet's infrared phase curve would change. A phase curve measures the total brightness from the planet star system as the planet moves through its orbit. The principle is related to the phases of the moon. When we see a full moon, most of the illuminated lunar hemisphere is facing us. Near new moon, the illuminated hemisphere points mainly away from us. A distant exoplanet is too small to see as a detailed crescent or disk, but telescopes can still measure changes in the total light coming from the system. For a hot rocky world, infrared measurements are particularly useful because the planet emits thermal radiation. As Kuaꞌkua travels around Batsu, we see changing portions of its hot and cold hemispheres. Near the part of its orbit where the dayside faces Earth, the planet contributes more infrared radiation. When the nightside faces us, the contribution drops. The exact shape of that rise and fall contains information about the planet's temperature distribution. The 2019 Spitzer data already showed a thermal pattern that looked like a strongly irradiated bare rock with little heat reaching the nightside. Years later, researchers returned to those measurements with a more detailed question. Could the data tell us how the planet rotates? The 2024 analysis modelled Kuaꞌkua as an atmosphere-free world and tested different rotational possibilities. One of the alternatives was rapid, non-synchronous rotation. Another was a 3-to-2 spin-orbit resonance like Mercury's. Mercury is not synchronously locked to the Sun. It rotates 3 times for every 2 orbits. One Mercury year lasts about 88 Earth days, while one rotation relative to distant stars lasts about 59 days. That 3-to-2 relationship is stable because Mercury has an eccentric orbit and because the planet is not perfectly spherical. So it was reasonable to ask whether Kuaꞌkua might occupy something similar. Perhaps it was close to its star but not actually locked in a one-to-one relationship. Perhaps its surface was still cycling through daylight and darkness. The thermal data argued against that. The researchers found that rapid non-synchronous states, including a Mercury-like 3-to-2 resonance, would produce substantial tidal heating under the conditions required to maintain them. That heating would alter the planet's thermal emission. The expected signal was not present. Their models instead supported synchronous rotation. The same work also placed an extremely tight limit on Kuaꞌkua's orbital eccentricity, finding it below about 0.001. That means the orbit is very nearly circular. For comparison, Mercury's orbital eccentricity is about 0.206. Earth's is around 0.017. Even Io, the intensely volcanic moon of Jupiter whose slight orbital eccentricity helps generate enormous tidal heating, has an eccentricity of roughly 0.004. Kuaꞌkua appears to travel around Batsu on an orbit more circular than Io's. That matters because eccentricity can keep tides active. If an orbit is noticeably elliptical, the distance between planet and star changes during each orbit. The strength of the tidal pull changes with it. The planet is repeatedly flexed. Io provides an extraordinary example close to home. Jupiter's gravity continually deforms the Moon as Io moves through its slightly eccentric orbit. That deformation generates heat inside Io. and helps power the most intense volcanic activity known in the solar system. Kuaꞌkua is close enough to Batsu that tidal heating could also matter if the orbit was sufficiently eccentric, or the rotation remained significantly out of synchronization. But the observations do not show the level of excess heating expected from those more energetic states. The simplest interpretation is that the system has already done what tidal evolution tends to do. The orbit became extremely circular. The rotation settled into synchronization. The same hemisphere remained facing Batsu. In 2024, this evidence was described as the first convincing empirical confirmation that an exoplanet has a permanent nightside caused by one-to-one tidal locking. We are not seeing the planet as a globe and literally watching one face remain pointed toward the star. The evidence comes from thermal measurements and physical modelling, but it is considerably stronger than simply saying tidal locking is theoretically expected. Later Webb observations have continued to use this synchronized picture when interpreting Kuaꞌkua's surface emission. The 2026 mid-infrared spectrum is best explained by a dark, low-silica rocky surface, with no evidence for accumulated volcanic gases forming a substantial atmosphere. The surface appears old and probably space-weathered, which fits naturally with a world that has spent a very long time exposed directly to its stellar and space environment. What would synchronous rotation actually feel like on the ground? The answer depends entirely on where you stood. Begin at the substellar point. This is the location on the surface directly facing Batsu. There the star would remain roughly overhead, not for 11 hours, not for a season. It would occupy essentially the same region of sky continuously. Kuaꞌkua would complete an orbit, then another, then another. From distant space, the planet would have travelled around its star many times, but at the substellar point Batsu would continue shining from nearly the same direction. Move away from that point and the star would appear lower. At a location halfway toward the boundary with the nightside, Batsu might remain at a fixed angle above the horizon. Continue farther and the star would sink lower still. Eventually you would reach the terminator, the dividing region between direct starlight and darkness. There, Batsu would remain close to the horizon, cross onto the nightside and it would disappear completely. Walking farther would not make it rise later. Waiting would not help. The planet's 11-hour orbit would continue, but local sunlight would be controlled by position on the surface. On Earth, longitude helps determine when the sun rises. On Kuaꞌkua, longitude could determine whether it rises at all. That changes the meaning of east and west in an interesting way. On Earth, travelling east or west changes local solar time because different longitudes rotate into sunlight at different moments. On a synchronized planet, travelling toward or away from the substellar region changes the permanent position of the star. You could, in principle, move from a place where Batsu sits high in the sky to one where it appears near the horizon without waiting for the sky itself to change. Of course, describing the star as perfectly motionless is an idealization. Real orbital systems are not mathematical diagrams. A small amount of orbital eccentricity can create slight apparent east-west motion called optical libration. A non-zero axial tilt could introduce north-south variations. The planet can also experience physical libration, tiny oscillations around exact synchronous orientation. Our own moon does this, which is why, over time, observers on Earth can actually see about 59% of the lunar surface rather than exactly 50%. Kuaꞌkua's very low inferred eccentricity suggests that any comparable orbital rocking should be limited, and the basic permanent day/permanent night arrangement remains the important picture. The planet may wobble slightly. It does not appear to be turning every longitude through ordinary days and nights. That long-term stability matters for the surface. On Earth, the ground receives solar heating during the day and releases energy at night. The cycle repeats. Temperature changes are moderated by atmosphere, oceans, clouds, vegetation, soil, and the thermal properties of the surface itself. Kuaꞌkua does not appear to have most of those buffers. At the substellar region, energy continues arriving. Rock absorbs it and heats until outgoing thermal radiation can balance much of the incoming energy. Near the night hemisphere, direct stellar input falls to zero. Without a substantial atmosphere to transport large amounts of heat, the temperature contrast becomes enormous. Research into tidally locked rocky planets shows that such a permanent difference in surface heating can even influence what happens beneath the crust. Recent modelling of tidally locked planetary mantles has examined how a very hot substellar hemisphere and a cold antistellar hemisphere can produce internal circulation patterns unlike those inside Earth. For LHS 3844b, specifically, researchers use an approximate 1000 Kelvin contrast between the substellar and antistellar regions as an example of the extreme thermal forcing these worlds can experience. So tidal locking is not merely something that happens in the sky. It can affect the surface. It can affect temperatures. It can influence atmospheric circulation when an atmosphere exists. It may influence the way heat moves through a planet's interior. It can shape where rock melts, where volcanic activity is favoured, and how different regions evolve over geological time. The simple phrase, "one side faces the star," hides a planetary scale rearrangement of energy. It is also worth separating tidal locking from habitability in general. A tidally locked planet is not automatically lifeless. There has been considerable research on planets in the habitable zones of red dwarfs where permanent day and night could coexist with substantial atmospheres. A thick atmosphere can redistribute heat. Oceans, if present, can transport additional energy. Clouds can form over strongly heated regions and alter how much starlight reaches the surface. Under the right conditions, a synchronously rotating planet could have moderate temperatures over large areas. Kuaꞌkwa is not such a case. It is far too close to Batsu, receives intense irradiation, and apparently lacks the thick atmosphere that would soften the day-night contrast. The tidal locking itself is not the main problem. The combination of locking, extreme stellar heating, and atmospheric absence is what creates the environment we're dealing with. In that sense, Kuaꞌkwa gives us a particularly clear version of a tidally locked world. There is little atmospheric weather to disguise the basic geometry. Batsu heats one hemisphere directly. The other receives no direct light. The exposed rocky surface responds. That simplicity is one reason the planet has become such a useful object for testing ideas that were once difficult to verify. Before the 2024 work, synchronous rotation among close-in rocky exoplanets was largely something astronomers expected from tidal theory. Kuaꞌkwa provided a way to check the expectation against observed heat. The result matched. A planet about 49 light-years away had given up enough information through infrared photons for us to infer that one hemisphere is permanently turned toward its star. There is something slightly strange about how ordinary that sentence can sound after repeating it a few times. We are talking about determining the rotation state of a rocky world that we cannot see as a resolved disk. We do not have photographs of its landscape. No spacecraft has visited it. Batsu itself is too faint to see with the naked eye from Earth. Yet the way Kuaꞌkwa warms and cools tells us that its surface does not rotate through ordinary dawns and sunsets. The rock has become the clock. Its temperature pattern keeps track of how the planet turns. And that pattern tells us that Kuaꞌkwa's two hemispheres have probably been living very different histories for an extremely long time. Consider what permanent really means on a planetary scale. Earth has deserts that remain dry for long periods. Polar regions can remain dark for months. Deep ocean floors never receive sunlight at all. But the whole planet is connected through an atmosphere, oceans, rotation, and climate. Kuaꞌkwa's illuminated hemisphere may have been directly exposed to Batsu for billions of years. The antistellar hemisphere may have spent the same period without a sunrise. A rock near the substellar point could exist beneath continuous stellar irradiation, while another rock on the opposite side, separated by only a few planetary radii, exists in a permanently dark environment. They belong to the same world. They complete every orbit together. They share the same gravity and interior. but the energy arriving from above is completely different. Even the boundary between the two is unusual. On Earth, the line between day and night travels continuously across the globe. At this moment, it is moving over oceans, cities, mountains, forests and deserts as Earth rotates. Every sunset is part of that moving boundary. Every sunrise is another. Viewed from space, the Terminator sweeps endlessly around our planet. On Kuaꞌkua, the Terminator is tied to the same broad region of the surface. Instead of the landscape passing through sunset, there is a landscape where the star is always near setting but never completes the process in the ordinary sense. Just beyond it lies permanent darkness. Just inward lies permanent illumination. The environment changes as you move across the planet rather than as you wait through the day. That fixed geography also means there is one region receiving the strongest direct energy from Batsu. At the substellar point, the star is highest in the sky, and stellar radiation strikes the surface most directly. If we move away from the geometry of tidal locking and imagine arriving over the hemisphere that faces Batsu, the first thing to understand is that daylight here does not behave the way daylight behaves on Earth. There is no morning. There is no afternoon moving gradually toward evening. The star does not rise from one horizon, cross overhead, and disappear behind the other. Instead, its position in the sky depends mostly on where you're standing. Near the center of the illuminated hemisphere, Batsu would remain high above the ground. Move farther away from that region, and it would sit lower in the sky. Continue toward the edge of the dayside, and eventually the star would appear close to the horizon. But if you stayed in one place, there would be no normal sunset waiting at the end of the day. The light simply continues. For billions of years, the same broad hemisphere of Kuaꞌkua has probably faced its star, receiving energy orbit after orbit while the planet completes one 11-hour year after another. That makes the dayside the most strongly heated part of the planet, and it gives us something unusual in exoplanet science. A rocky surface that is hot enough to glow strongly in infrared light, yet apparently not hidden beneath a substantial atmosphere. This is one reason Kuaꞌkua has become such a useful world to study. Usually when astronomers investigate a planet, the atmosphere is one of the main things they want to measure. Atmospheres contain information. They can tell us about temperature, chemistry, weather, clouds, and sometimes the history of a planet. But they also get in the way. If you want to know what the ground itself is made from, having kilometers of gas above it is a little inconvenient. Earth provides a good example. Imagine trying to determine the composition of the Sahara Desert from another star while looking through clouds, water vapor, carbon dioxide, oxygen, dust, and the rest of our atmosphere. You would have quite a lot to sort through before getting to the sand. Kuaꞌkua appears to have removed that particular problem. Its dayside seems to be largely exposed. The radiation coming from the surface can escape directly into space, carrying information about the temperature and physical properties of the rock itself. That does not make the planet pleasant. It does make it scientifically cooperative. The center of the dayside is the region that receives the strongest direct radiation from Batsu. This location is called the substellar point. If tidal locking is exact, the substellar point remains beneath roughly the same place in the star-facing sky. There, Batsu would appear almost stationary overhead. And although Batsu is a small, cool red dwarf compared with our Sun, Kuaꞌkua is so close to it that the surface receives tens of times more stellar energy than Earth receives from the Sun. The result is extreme heat. Measurements place the dayside temperature at around 1000 Kelvin, with current estimates near 985 to 1000 Kelvin for the thermal surface emission being discussed. Converted into a temperature more familiar to us, that is roughly 700 to 730 degrees Celsius, hot enough to make most Earth environments seem extremely mild. Aluminum melts at about 660 degrees Celsius. Lead melts at a little over 327. The hottest air temperature measured naturally at Earth's surface does not come remotely close. And yet Kuaꞌkua is not necessarily a planet covered by a global ocean of molten rock. That distinction matters. When people hear about a rocky world with a permanent dayside close to a star, The easiest picture is often a glowing landscape of lava stretching from horizon to horizon. Some exoplanets probably do have conditions approaching that description. Kuaꞌkwa appears to be cooler. Its surface is extremely hot, but models and observations indicate that large areas can remain solid. Basalt, for example, generally melts at temperatures well above 1,000 degrees Celsius, depending on composition and pressure. A surface around 725 degrees Celsius is severe enough to destroy almost any familiar living system, but ordinary silicate rock can remain rock. So instead of a permanent ocean of lava, the current picture is closer to an exposed, dark, intensely heated rocky surface. Something perhaps more like an exaggerated Mercury than a planet made entirely of magma. The comparison with Mercury is useful, though not exact. Mercury also has almost no substantial atmosphere. Its surface experiences large temperature differences. It is dark, rocky, heavily processed by impacts and the space environment. But Mercury still rotates relative to the Sun in a way that gives its surface both day and night. A solar day on Mercury lasts 176 Earth days, which is extraordinarily long, but sunset eventually arrives. Kuaꞌkwa's dayside does not receive that relief. The same regions remain exposed to Batsu. The surface therefore reaches a temperature determined by a balance. Energy arrives from the star. The rock absorbs some of it. The warmer the surface becomes, the more thermal radiation it emits into space. Eventually, at a given location, the outgoing energy can approximately balance the incoming energy. The surface does not simply continue getting hotter forever. This is the same basic reason Earth does not become warmer every day without limit. Our planet receives solar energy and also radiates energy back into space. The details are much more complicated here because we have an atmosphere, oceans, clouds, ice, vegetation, and weather. Kuaꞌkwa appears to offer a much cleaner version. Light arrives, rock absorbs it, rock heats, rock radiates infrared energy back into space. At the substellar region, incoming radiation is strongest because the light strikes the surface more directly. As you move away from that point, the star sits lower in the sky. Its energy arrives at an increasing angle and spreads over a larger area. Heating becomes weaker, so there is no single temperature for the entire dayside. The central region is hottest. Temperatures decrease toward the permanent boundary with darkness. The landscape, whatever its exact appearance, would therefore contain a broad thermal gradient, even though the star itself barely moves in the sky. One region might remain extremely hot while another, thousands of kilometers away, is much cooler simply because Batsu sits nearer the horizon there. On Earth, we often associate temperature changes with time. Morning warms into afternoon, evening cools into night. Kuaꞌkwa replaces much of that daily change with geography. To find cooler ground, you do not wait until evening. You travel away from the point facing the star. And if you could keep travelling, Batsu would gradually descend without time being responsible for it. The angle changes because you're walking around the curvature of the planet. This would make the dayside visually unusual as well. Assuming the planet truly lacks a significant atmosphere, there would be no ordinary blue, orange or red sky. Earth's atmosphere scatters sunlight. Blue wavelengths scatter strongly, filling the sky with the familiar colour we see during the day. Near sunset, sunlight takes a longer path through the atmosphere, and more of the blue light is scattered away, leaving reds and oranges. Remove the atmosphere, and those effects largely disappear. Apollo astronauts standing on the moon saw a black sky, even while the lunar surface was brilliantly illuminated by the sun. Kuaꞌkwa's dayside would likely have the same basic contrast. Dark space overhead, direct light from Batsu, hot rock beneath it. No blue dome, no ordinary clouds, no atmospheric haze softening the distance, no familiar sunset colours near the terminator. Batsu itself would look very different from our Sun. It is a cool M-dwarf with a surface temperature around 3000 Kelvin, rather than the Sun's roughly 5800 Kelvin. its light is weighted more strongly toward red and infrared wavelengths. Human eyes, if they could somehow survive there and work normally, would therefore experience illumination different from Earth daylight. But it is worth being careful about imagining everything drenched in bright red like a science fiction film. Red dwarfs do not emit only red light. They emit across a range of wavelengths, including visible light. The exact colours of the illuminated landscape would depend on the star's spectrum, the minerals on the ground, their temperature, and the way human vision responded under those conditions. What we can say more confidently is that the star is cooler and redder than the Sun, and much of its output lies at longer wavelengths. The ground itself appears dark. That is one of the most important things Webb has now told us. In 2026, astronomers reported observations made with the Mid-Infrared Instrument, or MIRI, aboard the James Webb Space Telescope. They measured thermal emission from Kuaꞌkwa between roughly 5 and 12 micrometers. These are infrared wavelengths invisible to human eyes, but they are exactly where a hot rocky surface can reveal useful information. Different minerals do not emit thermal radiation in precisely the same way at every wavelength. The shape of the spectrum can therefore act as a fingerprint. Not a perfect fingerprint where one line instantly identifies one rock, but enough of a pattern for scientists to compare the data with laboratory measurements and physical models. The result did not favour a bright silica-rich surface resembling the more evolved continental crust found on Earth. Instead, the spectrum was best matched by darker, lower silica materials. Basalt is one possibility. Olivine-rich mantle material is another. Both are familiar types of planetary material. Basalt forms when certain magmas cool and solidify. Earth's ocean floor is largely basaltic. The dark plains visible on the Moon contain basalt produced by ancient volcanic eruptions. Large portions of Mars are basaltic. It is one of the most common volcanic rocks in the solar system. Olivine is also common. It is a magnesium and iron-rich silicate mineral found in Earth's mantle and in many meteorites. If you could somehow pick up a fresh piece of olivine-rich rock, parts of it might have a greenish appearance. That does not mean Kuaꞌkwa is a giant green planet. Surface texture, composition, iron content, irradiation, temperature, and billions of years of space weathering can change what the ground looks like. Webb's measurements point more generally toward a dark mafic or ultramafic surface, rather than something resembling Earth's silica-rich continental crust. That difference can tell us something about planetary history. Earth's continents contain large amounts of relatively silica-rich rock, because our planet has experienced a long and complicated geological evolution involving melting, differentiation, water, volcanism, and plate tectonics. Continental crust is not simply the default surface every rocky planet receives. It is the result of geological processes. Kuaꞌkwa may never have developed anything comparable, or later processes may have removed or buried such material. The Webb spectrum does not give us a complete geological history, but it does make some possibilities less likely. The exposed dayside does not look like a planet covered in fresh granite-like continental material. It looks much more compatible with darker rock associated with mantle-derived material and basaltic volcanism. There is another clue hidden in how featureless the spectrum appears. A fresh fine powder can produce stronger spectral signatures than a darkened, weathered surface. The Webb observations did not fit fresh powdered rock particularly well. An old surface altered by long exposure to space is more consistent with the measurements. That brings us to space weathering. Despite the name, this has nothing to do with rain forecasts. Space weathering describes physical and chemical changes to exposed planetary surfaces caused by things such as micrometeorite impacts, energetic particles, and radiation. On Earth, the atmosphere protects the ground from much of this. It also gives us ordinary weather, which rapidly alters exposed material through water, oxygen, wind, temperature changes, and biological activity. On an airless world, the surface interacts directly with space. Tiny impacts strike the ground. radiation affects mineral grains. Particles from the star hit exposed material. Over long periods, these processes can change how the surface reflects and emits light. The Moon shows clear examples. Lunar soil that has spent a long time exposed at the surface can look different from fresh material uncovered by a recent impact. Mercury's surface has also been altered by long exposure to the solar environment. Kuaꞌkwa may have experienced its own much more intense version of this. It orbits extremely close to a red dwarf. There is little atmosphere to stand between the rock and the star. The same hemisphere remains facing Batsu, and the system is billions of years old. So whatever the dayside looked like when the planet was young, the surface we detect now may have been processed for an immense amount of time. That does not mean every stone has sat untouched for nearly 8 billion years. Impacts could excavate new material. Volcanism may have resurfaced portions of the planet in the past. Rock could fracture. Crust could be rearranged by internal processes. But the overall spectral appearance is consistent with an old, dark, exposed surface rather than a recently refreshed bright landscape. The lack of detected volcanic gases adds another piece to this picture. Webb's spectrum placed strong limits on gases such as carbon dioxide and sulfur dioxide. The data do not show an atmosphere built up from volcanic outgassing. That is interesting because rocky planets can release large quantities of gas from their interiors. Earth has done so throughout its history. Venus has a massive carbon dioxide atmosphere. Volcanoes on Earth release carbon dioxide, sulfur compounds, water vapor, and other gases. If Kuaꞌkwa were volcanically releasing enough material and that gas remained around the planet, astronomers might expect some atmospheric signature. So far, they do not see one. That could mean current volcanic activity is limited. It could mean gases escape efficiently. It could mean volcanic activity occurred in the past, but not at a level that maintains an atmosphere today. The measurements do not allow us to stand on Kuaꞌkwa and count active volcanoes. They simply tell us that the atmosphere we might expect from strong accumulated outgassing is not there. There is also an important difference between the temperature of the rock and whether the rock glows visibly. At around 1000 Kelvin, some of the hottest material could begin emitting a faint visible glow at longer wavelengths, although most of the thermal energy would still come out in the infrared. A blacksmith heating metal gives us a rough comparison. As an object becomes hot enough, it begins to glow dull red. Increase the temperature and it becomes brighter. The surface of Kuaꞌkwa is not a metal bar in a forge, and temperatures vary considerably across the hemisphere, but the physics is related. Every object above absolute zero emits thermal radiation. You do, your walls do. Your pillow does. Most objects around you are simply too cool for that radiation to be visible, so they glow mainly in infrared wavelengths. Kuaꞌkwa is hot enough to emit far more strongly. That infrared glow is what allows a telescope dozens of light years away to study the surface. The planet effectively tells us about itself by radiating heat. Astronomers do not need to see individual rocks. They measure the combined infrared light from an entire hemisphere and compare its wavelength pattern with what different surfaces should produce. It is a little like trying to determine what an enormous stove is made of by measuring its heat from across a city, except the stove is 49 light years away and circling a star every 11 hours. The fact that the measurement works at all is remarkable. During a secondary eclipse, Kuaꞌkwa passes behind Batsu from our point of view. Before the eclipse, the telescope receives light from the star plus thermal radiation from the planet's dayside. Then the planet disappears behind the star. For that brief period, its contribution is removed. The telescope measures the star alone. Subtract one measurement from the other very carefully, and the missing light belongs to the planet. That small difference contains the spectrum of a world. Nothing has photographed the basalt directly. There is no close-up view of a Kuaꞌkwa crater. Instead, scientists measure what disappears when the planet slips behind its star. It is a clever method because the star itself provides the reference. Planet visible, star plus planet. Planet hidden, star. The difference is Kuaꞌkwa. Of course, the measurement is not as simple as those 3 sentences make it sound. Telescopes have instrumental noise. Stars are not perfectly constant. Data must be calibrated. Models must account for temperature, viewing geometry, surface texture, and multiple possible compositions. Different materials can produce similar spectra. The result is therefore not, "We found this exact rock sitting at this exact location." It is a set of constraints. Some surfaces fit the data, others do not. Basalt and other olivine-rich, low silica materials fit well. Bright evolved crusts fit poorly. Fresh fine powders are disfavoured unless space weathering has changed their optical properties. A substantial atmosphere is not required and is strongly restricted by the observations. That is what modern exoplanet geology often looks like, not a photograph. A process of eliminating possibilities until the remaining physical picture becomes increasingly specific. And the picture of Kuaꞌkua's dayside is becoming clearer. It is hot. It is dark. It appears largely airless. It is probably rocky throughout. Its exposed surface likely contains basaltic or mantle-like material. It has probably been altered by long exposure to space. The centre of the dayside receives the strongest irradiation. The ground becomes progressively cooler toward the terminator. There is no ordinary water cycle. No rain is falling onto the hot rock. No ocean is carrying heat toward the other hemisphere. No wind is taking warm air toward the dark side because there does not appear to be enough air for that kind of circulation. That absence of wind would make the landscape strangely still. On Earth, even barren deserts are active. Dust moves. Air pushes against rocks. Temperature differences drive convection. Clouds cross the sky. Sound travels through the atmosphere. Kuaꞌkua could have an exposed surface where none of that happens in the familiar way. Without an atmosphere, ordinary sound would not travel through open space above the ground. If a rock fell beside you, vibrations could move through the surface itself, but there would be no air carrying the sound to your ears. A large impact could release enormous energy and still produce no rolling atmospheric thunder. Dust blasted upward could follow ballistic paths and fall back rather than becoming suspended in wind. A human visitor standing there inside an absurdly capable protective suit might see an event that looked violent and hear very little except vibrations transmitted through the suit and the ground. The star would remain above. The sky would remain dark. The ground would continue radiating heat. Even shadows would behave differently from what we expect. At the substellar point, objects would cast shadows mostly beneath themselves because Batsu sits high overhead. Farther toward the edge of the dayside, shadows would become longer because the star is lower, but the shadows would not sweep steadily across the landscape as the hours passed. A boulder might cast approximately the same shadow direction year after year after year. Small librations or orbital variations could shift the illumination slightly, but nothing resembling Earth's daily march of shadows would occur. A cliff could leave the same nearby ground shaded for extraordinarily long periods. A crater wall might protect parts of its interior from direct stellar radiation. Local topography would therefore matter. Permanent illumination does not mean every square meter of the dayside is continuously exposed to the star. Mountains create shadows. Crater walls block light. Caves remain dark. A deep enough depression near the terminator could contain areas that receive very little direct radiation. The surface temperature could therefore vary on smaller scales as well as across the hemisphere. This is familiar from the Moon and Mercury, where topography creates permanently shadowed regions near the poles under suitable illumination geometry. On Kuaꞌkua, the geometry would be different because the whole planet is synchronized to the star, but the principle remains simple. Light travels in straight lines. Rock gets in the way. So even on the hemisphere of eternal day, darkness would exist in shadows. It simply would not arrive because of sunset. Those cooler regions raise interesting questions about how the crust responds to the enormous temperature differences across the planet. Rock expands when heated and contracts when cooled. On Earth and the Moon, Repeated heating and cooling can contribute to mechanical breakdown. Kuaꞌkua's tidally locked surface does not experience a normal daily cycle, but different locations sit at very different long-term temperatures. The hot substellar region and the cold nightside belong to a continuous rocky shell. Heat can move through that shell by conduction. The interior can transport energy through mantle convection. Large thermal differences may affect stresses in the crust and patterns of internal circulation. Models of tidally locked rocky planets suggest that strong day-night contrasts can influence mantle dynamics, potentially producing geological patterns unlike those on Earth. But the observations do not yet give us a detailed tectonic map. We do not know where Kuaꞌkua's mountains are. We do not know whether enormous ancient lava plains cover one hemisphere. We do not know whether impact craters dominate the landscape. Webb has given us broad information about the surface's infrared behaviour and likely composition, not a geological atlas. That distinction is worth keeping clear because it is easy to move from what we know into what we can imagine. What we know is already interesting enough. A rocky planet roughly 30% larger than Earth is circling an M-dwarf in 11 hours. Its star-facing hemisphere sits around 1,000 Kelvin. It does not appear to possess a significant atmosphere. Its exposed surface is dark and best matched by basaltic or olivine-rich material rather than bright silica-rich crust, and from dozens of light-years away, a telescope can detect radiation coming directly from that rock. Perhaps the strangest thing about the dayside is how stable its basic arrangement may be. Here on Earth, extreme conditions usually change. Heat waves end, night arrives, seasons move, storms pass. Even a desert at noon eventually becomes a desert at midnight. Kuaꞌkua's star-facing side does not receive that daily reset. The surface reaches its local balance with the incoming radiation and remains under essentially the same stellar geometry. Batsu completes no journey across the sky. It simply remains there while the world turns exactly enough to keep facing it. The same lack of atmosphere that allows Kuaꞌkua's dayside to become intensely hot also creates a very different environment on the hemisphere turned away from Batsu. Cross far enough beyond the edge of direct starlight, and the red dwarf disappears. It does not set in the way the sun sets on Earth. There is no evening followed by midnight, and then a gradual brightening in the east. Batsu is simply below the horizon because this part of the planet faces away from it, and the synchronized rotation keeps it there. An 11-hour year passes. The star does not rise. Another orbit follows. Still nothing. Days, years, millions of Kuaꞌkua orbits can pass without producing a morning. That is the basic condition of the nightside, and it is easy to underestimate how unusual it would be, because darkness on Earth is always connected to temporary absence. Even in places that experience long polar nights, the sun eventually returns. The geometry changes with the season. Daylight moves north or south, and the darkness ends. Kuaꞌkua offers no seasonal promise of dawn. For the broad hemisphere centered on the point directly opposite Batsu, darkness is part of the geography. If the dayside is defined by continuous irradiation, the nightside is defined by the absence of it. No direct stellar energy reaches the ground. That makes the nightside much colder than the illuminated hemisphere, especially because Kuaꞌkua does not appear to possess the kind of atmosphere that could transport large quantities of heat around the planet. Spitzer gave astronomers the clearest early evidence of this contrast. As Kuaꞌkua moved around Batsu, the telescope measured the combined infrared light coming from the system. When the hot dayside faced Earth more directly, the planet contributed more thermal radiation. When the nightside rotated into our view because of the planet's orbital position, that contribution dropped dramatically. The dayside brightness temperature at the observed wavelength was about 1040 Kelvin. The nightside signal was consistent with zero thermal emission within the uncertainty of that particular measurement. That last sentence needs to be handled carefully because it is very easy to turn an observational statement into something much stranger than the science actually says. The nightside is not believed to be at 0 Kelvin. 0 Kelvin is absolute zero. the lower limit of temperature, and Kuaꞌkua's dark hemisphere is not a perfectly frozen object containing no thermal energy. What the Spitzer result means is that the telescope did not detect a significant nightside signal at 4.5 micrometers. Within the sensitivity and uncertainty of those observations, the nightside was too faint to measure clearly. That still tells us a great deal. If Kuaꞌkua had a thick atmosphere efficiently carrying energy from the dayside, the dark hemisphere should have been much warmer. Warm air would move away from the illuminated side, cooler air would return. Large-scale winds could redistribute some of the energy received beneath Batsu. The night side would then emit more infrared radiation. Spitzer did not see the level of heat expected from that kind of atmospheric circulation. Instead, it saw an enormous contrast. One half of the planet was glowing strongly in infrared. The other was barely visible thermally at that wavelength. That is exactly the kind of behaviour we expect from an exposed rocky world where stellar heating remains concentrated on the hemisphere that actually receives the starlight. Earth would behave very differently. When night falls outside your window, the surface does not immediately collapse toward the temperature of deep space. The ground spent the day absorbing sunlight. Buildings stored heat. Oceans hold enormous amounts of energy. The atmosphere moves warm and cold air over huge distances. Clouds absorb and re-emit infrared radiation. Water vapour and other gases slow the escape of heat. The entire planet is connected by a moving atmosphere and ocean system. Even the coldest places on Earth remain influenced by energy that arrives somewhere else. Kuaꞌkua appears to have very little of that assistance. If its atmosphere is as thin as current observations suggest, then there is no major global wind system transferring dayside heat across the terminator. There are no oceans carrying warm water into darkness. There is no thick cloud layer trapping infrared radiation. The nightside has to live mainly on whatever energy can reach it through the solid planet itself, whatever internal heat still escapes from below, and whatever extremely limited mechanisms remain. That does not make the nightside completely isolated. Kuaꞌkua is one continuous body. Rock on the dayside is connected to rock on the nightside. Heat can conduct through solid material. The planet's interior can move energy through mantle convection. Radioactive elements, if present as they are on Earth and other rocky bodies, release heat as they decay. Energy remaining from the planet's formation can also contribute to internal warmth over geological time. There may be some residual tidal heating, although observations suggest that Kuaꞌkua's orbit is extremely circular and its rotation is synchronized, which reduces the sort of strong ongoing tidal flexing seen on a moon like Io. So the dark hemisphere is not thermally disconnected from the universe. It is simply missing the overwhelmingly important energy source that dominates the dayside, direct radiation from Batsu. The surface temperature would also vary across the nightside. It would be misleading to imagine one perfectly uniform frozen hemisphere. Near the terminator, heat from nearby illuminated terrain can conduct through the ground. Topography matters, rock type matters, thermal conductivity matters, subsurface temperature matters. Farther into the nightside, direct influence from the dayside becomes weaker, and the surface should become colder. The coldest broad regions would be expected near the antistellar point, the location directly opposite Batsu. If the substellar point is permanent noon, the antistellar point is the closest thing Kuaꞌkua has to permanent midnight. Stand there, and Batsu is not merely below the horizon. It is on the opposite side of the planet. A straight line from your feet through the centre of Kuaꞌkua would point roughly toward the star. The entire mass of the planet would sit between you and its light. That makes the antistellar region very different from ordinary midnight on Earth. At midnight here, the Sun is also on the opposite side of the planet, but Earth keeps rotating. 6 hours later, your location has moved a quarter turn. Another 6 hours and daylight has returned. The coldest part of the night is temporary. On Kuaꞌkua, rotation does not carry the antistellar surface toward dawn. The planet turns once every orbit, but it turns at exactly the rate needed to keep that region facing outward. Batsu remains hidden behind thousands of kilometers of rock. Even the stars above would behave in an unfamiliar way. On Earth, the night sky appears to rotate because our planet turns beneath it. Stars rise in the east and set in the west, while the exact pattern depends on latitude. Kuaꞌkua does rotate relative to distant stars, and it does so once every 11 hours. So the nightside sky would not necessarily be completely fixed. Distant stars could move across the sky as Kuaꞌkua rotates and orbits, even while Batsu remains permanently excluded from view. That distinction is important. Tidal locking fixes the direction of the host star relative to the surface. It does not freeze the entire universe overhead. An observer on the night side could watch the wider galaxy move through the sky, while the system's own star never appeared. The sky itself would be black. Without a significant atmosphere, there would be no blue scattering during the day and no atmospheric glow at night. There would also be no weather in the familiar sense, no clouds drifting through the darkness, no wind moving across the plains, no fog forming in valleys, no snow carried sideways in a storm. If Kuaꞌkua possesses only an extremely tenuous exosphere, individual atoms or molecules might still exist above the ground, but that is very different from an atmosphere capable of creating ordinary weather. The landscape could therefore remain visually still for long periods. A crater would not slowly fill with wind-blown sand in the way a depression might on Mars. Dust disturbed by an impact would follow paths governed largely by gravity before falling back. Fine material could remain where impacts, fractures, and other geological processes left it. And if you were standing on the night side inside an imaginary suit capable of keeping you alive, the darkness would not necessarily be complete. The stars would provide some light. The Milky Way could be visible if the local orientation allowed it. Other planets, if the Batsu system contains them, and if they were bright enough, might occasionally appear as moving points. Meteoroid impacts could produce brief flashes. Hot material exposed by an impact or volcanic event could glow. But there would be no moon unless Kuaꞌkua happens to possess an undiscovered satellite, and a close-in planet like this is not an easy place for a moon to maintain a stable orbit. More importantly, there would be no bright host star dominating the sky. The primary source of energy for the system would remain on the other side of the world. That separation would make temperature and illumination strongly dependent on where you travel. Imagine beginning on the night side near the anti-stellar point and moving steadily toward the terminator. At first, nothing about the position of Batsu would change visibly, because the star remains far below the horizon. The ground might gradually become warmer as you approach regions closer to the permanent dayside. The terrain itself could change if different temperatures have influenced the crust over geological time. Shadows would remain meaningless in the ordinary sense because there is no direct stellar beam to cast them. After travelling thousands of kilometres, the first sign of Batsu would not be a dawn produced by time, it would be produced by movement. You have carried yourself around the curvature of the planet until the star is no longer hidden by the ground. That is an important difference. On Earth, we normally wait for sunrise. On Kuaꞌkua, you would travel toward it. Stay still, and nothing happens. Walk far enough in the correct direction, and morning becomes a place. This creates an odd relationship between distance and daylight. A traveller could move from permanent darkness toward permanent illumination, crossing environments that on Earth would be separated by hours of time. There could be a region resembling very deep pre-dawn darkness. Then Batsu might appear barely above the horizon. Continue toward the substellar point and the star would climb higher, not because the planet's day is progressing, but because the ground curves beneath your path. At every location, the star has its own approximately fixed place in the sky. That arrangement also produces large long-term temperature differences in the crust. The dayside surface may remain hundreds of degrees above the temperatures found deep in the dark hemisphere. Rock is not a perfect insulator, so heat tries to flow from warmer regions toward cooler ones. But conduction through thousands of kilometers of planetary crust and mantle is not remotely as effective as an atmosphere transporting heat above the surface. Solid rock moves energy slowly. This is why caves on Earth can maintain temperatures different from the surface, and why daytime heat does not immediately penetrate very far into the ground. The deeper you go, the less important short-term surface temperature changes become. Kuaꞌkwa does not have a normal day-night cycle, so its underground temperature structure would be different, but the same basic rule applies. Surface conditions do not instantly determine the temperature of the entire planet below. The permanent night side could therefore have a cold upper surface over warmer material at depth. Go downward and heat from the planetary interior eventually becomes more important. Earth works this way too. A winter night may freeze the ground at the surface, but deep mines become warmer as depth increases because of geothermal heat. Kuaꞌkwa's dark hemisphere may have its own geothermal gradient. We do not know the exact value. We do not have measurements from boreholes, obviously, and the interior structure is inferred rather than directly sampled. Recent mass measurements indicate that Kuaꞌkwa is a dense rocky planet, a little more than twice Earth's mass, so there is plenty of interior rock beneath the cold surface. What we cannot currently say is exactly how much internal heat remains, how vigorous mantle convection is, or whether the night side hosts active volcanism. Those questions are especially interesting because volcanism could create temporary local exceptions to the overall cold environment. Suppose magma rose beneath the permanent night side. The surrounding ground might be extremely cold by planetary standards, but molten rock arriving from the interior would carry its own heat. An eruption could create a glowing patch in an otherwise dark landscape. Lava could cool rapidly at the exposed surface while remaining molten underneath. Gases released during eruption might briefly create a local cloud of material before being lost, condensed, or redistributed. Nothing in the current observations allows us to say that such eruptions are happening now. Webb has not found evidence for accumulated volcanic gases such as a substantial carbon dioxide or sulfur dioxide atmosphere. That absence actually suggests that strong continuous outgassing has not built a persistent blanket of gas around the planet. But a lack of accumulated atmosphere does not prove that every volcano has been extinct for billions of years. It tells us that whatever the geological activity may be, it has not produced a detectable thick atmosphere of the kinds tested by current observations. The night side could also preserve materials differently from the day side. On the illuminated hemisphere, the surface is exposed continuously to strong stellar radiation and high temperatures. On the dark hemisphere, there is no direct starlight. That could change how minerals weather. High-energy particles from space can still reach the surface. Cosmic rays do not care whether it is daytime. Charged particles from Batsu can interact with the planetary environment in complicated ways, especially if Kuaꞌkwa lacks a protective global magnetic field. Micrometeorites can strike anywhere, but direct thermal processing by the star is absent. If volatile material somehow existed on Kuaꞌkwa, the night side would be the obvious place to ask whether they could condense. This requires caution, because we do not have evidence that Kuaꞌkwa currently possesses large stores of water, carbon dioxide, ice, or other familiar volatiles sitting on its night side. Recent interior modelling also favours a dry, rocky composition with only limited room for water in the planet's bulk makeup, and the intense history of irradiation makes long-term retention of volatile materials difficult. Still, the physics is straightforward. A molecule that would remain gaseous or be destroyed on the hot day side could behave very differently in a cold, permanently dark region. On some tidally locked planets with atmospheres, scientists worry about atmospheric collapse. If the night side becomes cold enough, major atmospheric gases can condense or freeze onto the surface. The gas moves from the day side to the night side, cools and becomes trapped. If enough of it condenses, atmospheric pressure falls. Kuaꞌkwa appears to have gone much farther than that simple scenario because observations already favour little or no substantial atmosphere. But the night side remains part of the reason atmospheric survival is difficult to understand. Any gas released from the interior would face very different conditions depending on where it travelled. On the dayside, heat and stellar radiation encourage escape and chemical processing. On the night side, low temperatures encourage condensation for some substances. A stable atmosphere has to survive both environments while circulating between them. Kuaꞌkwa seems not to have managed it, at least not at a level large enough for us to detect today. The absence of atmosphere also changes the way temperature itself should be imagined. On Earth, we usually speak about air temperature. 30 degrees Celsius means the air around you is warm. -10 means the air is cold. On an airless night side, there may be almost no meaningful air temperature at the surface because there is almost no air. Instead, temperature belongs mainly to the ground, rocks, dust, and whatever material happens to be present. Two nearby surfaces could have different temperatures depending on what they are made of and whether they receive radiation from a warmer object. This happens on the Moon. A sunlit surface can become extremely hot while a nearby shadow is much colder, because there is little atmosphere to smooth out the difference. Kuaꞌkwa takes that idea and extends it across an entire hemisphere. The darkness also means there is no atmospheric greenhouse effect comparable with Earth's. A greenhouse atmosphere absorbs some outgoing infrared radiation and emits part of that energy back toward the surface. Without that blanket, a surface can radiate heat directly into space. The night side is therefore efficient at losing whatever energy reaches its uppermost layers. A rock warmed by geothermal heat emits infrared radiation upward. Space provides almost nothing in return except the faint background radiation of the universe and energy from distant objects. The rock cools until incoming and outgoing energy reach balance. That balance would vary with location and with the strength of internal heat flow. One of the more surprising things about the Spitzer observation is how strongly it limits the amount of energy being shared between the two hemispheres. The planet is only about 30% larger in radius than Earth. Its hot and cold sides are separated by distances comparable with crossing a terrestrial planet. Yet thermally, they behave almost like different environments that have very little communication. That would not happen on Earth because the atmosphere constantly tries to erase temperature differences. Heat creates pressure differences. Pressure differences create winds. Winds move energy. The process never stops. Kuaꞌkwa lacks that global smoothing mechanism. The planet can therefore maintain a temperature structure that would be difficult to sustain here. Very hot rock on one hemisphere, very cold rock on the other. A transition between them fixed approximately in place. That makes the night side valuable to astronomers even though it is difficult to measure directly. A warm night side would immediately tell us that something is moving energy there. An atmosphere would be an obvious candidate. A large amount of tidal or geothermal heating could also contribute. The very weak measured nightside signal instead supports the simpler bare rock picture. In this case, darkness is not merely something we infer because tidal locking says the star should be absent. The thermal behaviour agrees. The hemisphere that receives no direct stellar energy is also much fainter in infrared. Geometry and temperature tell the same story. Future observations may improve the numbers. A more sensitive phase curve at additional wavelengths could place better constraints on the nightside temperature. Different infrared wavelengths probe thermal emission differently. Combining them could help separate surface composition from temperature and perhaps reveal whether some parts of the night side are warmer than the existing measurements suggest. That would let astronomers ask more detailed questions. How much internal heat reaches the surface? Does the temperature decline smoothly from the dayside into darkness? Are there asymmetries? Could geological activity produce warmer regions? Does the surface have different thermal properties on the two hemispheres? At the moment, we do not have answers detailed enough to draw a nightside map. We have the broad pattern, hot illuminated hemisphere, extremely weak thermal signal from the dark hemisphere, very little evidence for atmospheric redistribution, synchronous rotation keeping the two environments in place. That broad pattern is already enough to make Kuaꞌkwa different from almost every world people naturally imagine when they hear the word planet. Most fictional planets behave like Earth unless the story specifically needs something else. They have mornings, they have evenings. Travellers land beneath a sky, wait for night, and continue the next day. Kuaꞌkua would make that routine useless. If you landed near the anti-stellar point, waiting for daylight would achieve nothing. If your equipment depended on solar power, the problem would not be surviving until morning. The problem would be reaching the morning side of the planet. A rover designed for the night side would need its own energy source. Solar panels would remain decorative. Navigation would use stars, inertial systems, radio signals, or landmarks rather than the position of Batsu. Temperatures could require heating rather than cooling. Communicating directly with the station on the central dayside might even be difficult because the bulk of the planet would block a straight radio path, requiring relay satellites or surface stations. Everything about exploration would be shaped by the fixed division between the hemispheres. A nightside base, in some distant and extremely unlikely technological future, would at least avoid the brutal direct heating of Batsu. But that does not suddenly make the region comfortable. There is no breathable air. There appears to be almost no atmospheric pressure. The ground may be extremely cold. Radiation exposure would remain a concern. Meteorites would not burn up in an atmosphere before reaching the surface. Any human settlement would have to function more like a sealed spacecraft placed on rock than a town beneath a sky. The darkness would merely exchange one set of difficulties for another. And the deeper into that darkness you travelled, the farther Batsu would remain below the horizon. Eventually, though, travelling in the opposite direction would begin to change the environment. The surface would slowly become influenced by the permanently illuminated hemisphere ahead. Temperatures would rise. The direction toward Batsu would become meaningful even before the star itself appeared, because somewhere beyond the curvature of the ground lay rock receiving continuous stellar energy. Continue toward that boundary, and eventually darkness would stop being complete. The red dwarf would approach the horizon. That boundary is where Kuaꞌkua becomes especially easy to misunderstand. From a distance, a tidally locked planet seems simple enough. One hemisphere faces Batsu, the other faces away. Draw a circle, shade one half, leave the other bright, and place a neat line between them. Real planetary surfaces are not quite that tidy. Draw the boundary between locations that have a direct view of the star and locations where the star is below the horizon. Earth has a terminator too. At every moment, one side of our planet faces the sun while the other faces away, and the line separating them moves across the surface as Earth rotates. We experience that moving boundary as sunrise and sunset. On Kuaꞌkua, the basic geometry is different. Because the planet appears to rotate synchronously with its 11-hour orbit, the terminator remains tied to approximately the same longitudes. It does not sweep around the world every few hours. A location near that boundary can remain near it orbit after orbit. Batsu would stay low in the sky. Move slightly toward the dayside and it would rise higher. Move slightly toward the night side and it would disappear. Waiting in one place would do very little. That fixed boundary is sometimes described as twilight zone, but the word twilight can give the wrong impression. On Earth, twilight is created mainly by our atmosphere. After the sun has dropped below the horizon, sunlight still passes through the upper atmosphere. Molecules and particles scatter some of that light toward the ground, allowing the sky to remain bright for a while even though the sun itself is no longer visible. That is why sunset is not followed by instant blackness. Civil twilight fades into nautical twilight, then astronomical twilight, and eventually the sky becomes fully dark. Kuaꞌkua appears to lack the substantial atmosphere required for that kind of extended glow. Its 2019 Spitzer phase curve showed an enormous contrast between the hot dayside and the faint nightside, and the 2026 Webb spectrum found no evidence for an accumulated atmosphere while strongly limiting gases such as carbon dioxide and sulfur dioxide. You stood near the terminator, properly protected from several obvious problems. You probably would not see an Earth-like sunset stretching red and orange across a glowing sky. Batsu could sit just above a dark horizon. The ground receiving direct light would be illuminated. The sky around the star would still be black because there would be almost no air to scatter that light across the heavens. Take a few steps into the shadow of a sufficiently large ridge, and direct stellar illumination could disappear. The effect would resemble lighting on the moon much more than evening on Earth. Apollo astronauts could stand in brilliant sunlight while looking into a black sky. Shadows could become extremely dark because there was no thick atmosphere scattering light into them. Kuaꞌkua would likely exaggerate that basic arrangement on a much hotter and larger world. The exact terminator is a geometric boundary. On one side, Batsu is above the local horizon, on the other it is below it. Temperature is less abrupt. Rock does not become hundreds of degrees colder the instant you cross an imaginary line. The dayside surface has been heated for a very long time, and nearby material can transfer some energy through conduction. The planet's interior also contains heat. Terrain facing the star may remain warmer than terrain hidden behind a slope. Different minerals absorb and emit energy differently, so the transition from hot dayside to cold nightside would occupy a broad thermal region, even though direct starlight has a clear geometric limit. Imagine beginning near the substellar point, where Batsu remains highest in the sky. The surface there receives the strongest stellar heating. As you travel toward the terminator, the star gradually appears lower. The same amount of radiation leaving Batsu becomes spread over a larger area of ground. Because the rays arrive at an increasing angle, the heating therefore weakens. This is the same reason sunlight is generally less intense near Earth's poles than near the equator. A beam arriving almost vertically concentrates its energy over a smaller surface area. A beam arriving at a low angle spreads that energy across more ground. Kuaꞌkua turns that familiar effect into a permanent geographical pattern. Instead of the solar angle changing mainly with time of day and season, its broad pattern stays fixed. One region has permanent high-angle illumination, another has permanent low-angle illumination. Beyond the terminator, the direct stellar angle is gone altogether. If you could travel across the surface, you could choose the height of Batsu in your sky, simply by choosing where to stop. That does not mean every location at the same distance from the substellar point would have exactly the same temperature. A real landscape contains craters, cliffs, ridges, plains, rough rock, loose material, and surfaces tilted in different directions. A slope facing Batsu would absorb more direct radiation than a slope angled away from it. A crater close to the terminator could contain one wall permanently illuminated and another permanently shadowed. A boulder could cast a shadow that hardly changes direction for years. Some depressions might receive almost no direct stellar light, even though they lie technically on the dayside. Other high points could see Batsu from places where nearby lower terrain remains in darkness. The result would not be one simple ring with one convenient temperature. It would be a landscape of local thermal differences built on top of the much larger day-to-night gradient. This matters because the terminator of a tidally locked planet often appears in discussions of habitability. The idea is understandable. If the centre of the dayside is too hot and the centre of the nightside is too cold, perhaps the boundary between them is just right. It sounds like a planetary version of moving your chair away from the fireplace until the room feels comfortable. For some tidally locked planets, especially worlds in the habitable zones of cool red dwarfs with substantial atmospheres, scientists genuinely do investigate whether moderate conditions could exist near the terminator or over wider regions. Kuaꞌkua is not a good example of that hopeful scenario. It orbits far inside the region where an Earth-like amount of stellar energy would be received. Its dayside reaches temperatures around 1,000 Kelvin, and the observations favour a bare, dark, rocky surface, rather than a planet with oceans and a protective atmosphere. Can have a moderate surface temperature and still be extremely hostile. There is no detected breathable atmosphere. There is no evidence for surface water. There is no known pressure allowing liquid water to remain stable in the way it does across much of Earth. Stellar radiation reaches the surface with little atmospheric shielding. The nearby red dwarf has spent billions of years influencing the planet. So even if some strip of ground somewhere near the Terminator happens to pass through temperatures familiar to humans that would not turn it into a pleasant coastal climate, temperature is only one part of habitability. A vacuum at 20 degrees Celsius is still a vacuum. It is worth keeping that in mind because the word twilight has a way of making the place sound rather comfortable. What Kuaꞌkua offers is not necessarily a mild ring around a hot planet. It offers a fixed transition between two extreme energy regimes. On one side, direct radiation from Batsu dominates surface conditions. On the other, that source disappears. The transition is scientifically interesting precisely because Kuaꞌkua has so little atmosphere to smooth it out. Earth's atmosphere is constantly trying to reduce temperature differences. Warm air rises. Cooler air moves in. Winds carry energy. Ocean currents do even more work. A temperature contrast between one region and another can drive circulation that transports heat across continents and oceans. On Kuaꞌkua, the large amplitude of the measured thermal phase curve shows that heat is not being redistributed efficiently from day to night. The 2019 observations found a dayside brightness temperature of about 1040 Kelvin and a nightside signal consistent with 0 at the measured wavelength, while the phase variation remained approximately symmetric around the expected hottest region. Metry matters. If a strong atmosphere were carrying heat eastward or westward, the hottest region could shift away from the point facing Batsu. Hot Jupiters often show this behaviour. Their thick atmospheres can produce powerful winds that move the thermal maximum away from the substellar point. Kuaꞌkua does not show the same kind of obvious offset in the Spitzer phase curve. The heat pattern remains closely tied to direct stellar illumination. In practical terms, the surface near the Terminator does not receive a generous delivery of warmth from a global atmospheric circulation system. Whatever heat reaches it comes largely from its own weak direct illumination on the dayside edge, conduction through the rock, internal planetary heat, and thermal radiation from surrounding surfaces. Radiation between nearby terrain could matter locally. A warm cliff can radiate infrared energy toward another surface. A crater interior can exchange thermal radiation between its walls. But these effects are very different from a thick atmosphere carrying large quantities of heat, thousands of kilometers around the planet. The absence of substantial heat transport also raises questions about what the enormous temperature contrast does below the surface. Models of Kuaʻkua's interior have investigated whether permanent hemispheric heating could affect mantle convection. One study used the roughly 1000 Kelvin difference between the substellar and antistellar regions and found that such a contrast can produce hemispheric patterns of mantle flow that do not resemble the present-day tectonic behaviour of any planet in our solar system. Depending on the model assumptions, broad upwellings and downwellings could become organised differently beneath the hot and cold hemispheres. Know that Kuaʻkua actually has a particular tectonic pattern. There is no seismic network there. Nobody has placed GPS stations on opposite sides of the Terminator and watched the crust move. The modelling simply shows that the permanent temperature pattern could matter deeper than the top few centimetres of rock. On Earth, day and night alternate too quickly for ordinary daily heating to reorganise the mantle. The sun warms the surface, but mantle convection is driven by processes operating over enormous geological timescales and depths. Kuaʻkua presents a different boundary condition. One hemisphere has remained hot, the other has remained cold. The difference persists for geological time. That gives the interior much longer to respond. The Terminator could therefore represent more than a lighting boundary. It could separate regions whose crust and mantle have experienced different long-term thermal conditions. Perhaps volcanic history differed from one hemisphere to another. Perhaps the thickness or strength of the outer rock varies. Perhaps ancient lava flows were more common in particular regions. Those possibilities remain theoretical, and the 2026 Webb observations found no accumulated volcanic gases suggesting vigorous recent outgassing. The measured mid-infrared spectrum instead fits an old, dark, space-weathered surface, potentially made of basalt or other olivine-rich material. surface may preserve the effects of its strange lighting geometry for a very long time. Without rain, rivers, vegetation, and ordinary atmospheric erosion, landscapes do not change the way they do on Earth. Impacts can alter them. Thermal stresses can fracture rock. Space weathering can change the uppermost material. Past volcanism can cover older terrain. But a cliff near the Terminator does not have wind and rain gradually rounding it in the familiar terrestrial way. A permanent shadow could remain permanent unless an impact, landslide, volcanic event, or other geological process changes the landscape. The direction of direct stellar heating would remain almost unchanged. Kuaꞌkua's extremely low inferred orbital eccentricity helps keep that arrangement stable. A reanalysis of the Spitzer data found that the planet is consistent with synchronous rotation and constrained the eccentricity to below about 0.001. That is an orbit close enough to circular that large recurring variations in star-planet distance are not expected. Why still be small librations? Synchronous rotation does not require every point to maintain a mathematically perfect orientation for all time. The Moon wobbles slightly as viewed from Earth, allowing us to see more than exactly half of its surface over time. Kuaꞌkua could have its own small oscillations caused by its orbital and rotational properties. If so, Batsu might shift slightly near the horizon for locations close to the Terminator. A place right on the geometric boundary could occasionally receive a little direct light and then lose it again. But with such a nearly circular orbit, the broad division remains stable. This is not a planet where the Terminator sweeps across every longitude. Any motion would be a small variation around a fixed average pattern. That creates an interesting question about what it would be like to travel along the boundary rather than across it. Move toward the dayside and Batsu rises. Move toward the nightside and it disappears. Travel along the Terminator, however, and the star could remain near the horizon while the landscape changes beneath you. Because Kuaꞌkua is larger than Earth, this would be an enormous journey. Its radius is roughly 1.3 times Earth's, so a complete route around the planet near a great circle would cover more than 50,000 kilometers. The Terminator would extend around the entire world as a closed boundary, separating the illuminated hemisphere from the dark one. There would be no single east-side sunset and west-side sunrise as we have on Earth. It would form one continuous division around the globe. At different points along that route, local terrain could make the star visible or hide it. A mountain could catch direct light while a valley nearby remains dark. On elevated ground, the horizon is farther away, so Batsu could remain visible from a location where it has already disappeared for an observer lower down. That is ordinary geometry, but on Kuaꞌkua it becomes permanent geography. Earth has a similar effect for a few minutes at sunset. Climb a tall building after the sun has disappeared at street level, and you may be able to see it again because your higher horizon extends farther around the planet. Mountain peaks remain illuminated after valleys have entered shadow. On Kuaꞌkua, those few minutes could become a stable arrangement. One slope might live permanently in direct light while the ground behind it remains permanently shaded. If you stood in the shadow and climbed high enough, Batsu could reappear. Descend again, and it would vanish. No clock would be required. The local landscape would decide whether the star existed in your sky. The lack of atmosphere would make these lighting differences visually sharp. On Earth, indirect light fills shadows. The blue sky itself acts as a broad light source because sunlight has been scattered in every direction. Clouds reflect light. Dust and water droplets brighten the air. Even when direct sunlight is blocked, we're usually surrounded by illumination arriving from the atmosphere. Remove that atmosphere and shadows become much darker. The moon demonstrates this clearly. Kuaꞌkua's old dark surface could make the contrast even stronger. The star-facing side of a rock might be brightly heated while the opposite side receives little direct light. Near the Terminator, where Batsu sits low, small changes in terrain could produce long shadows extending across the landscape. A ridge only a few hundred meters high could block the star over a considerable area behind it. Craters would develop complex patterns of illumination, and because the star barely moves, those patterns could stay in place. This permanent low-angle illumination would also affect surface temperature. A rock facing Batsu could remain warmer than another rock a short distance away, whose orientation leaves it permanently shaded. Thermal conduction would gradually reduce the difference inside the material, but exposed surfaces could still maintain contrasting conditions. Loose regolith would respond differently from solid bedrock. Fine material generally has lower thermal conductivity and can insulate deeper layers. Solid rock transfers heat more efficiently. The 2026 Webb spectrum disfavors a surface dominated by fresh fine powder and instead supports an old, dark surface, although weathered powders cannot be completely excluded because space weathering can change their infrared properties. The texture of the ground matters when imagining the Terminator. A broad bare rock plain could conduct heat differently from a thick layer of loose debris. A crater excavating fresh material could expose rock with different thermal behaviour. An old impact basin might have cooled into a stable environment, unlike surrounding highlands. We simply cannot resolve those details from Earth. Webb measures the combined emission from large portions of the planet. It does not provide a photograph with individual terrain features. That leaves the Terminator as one of the places where the difference between measurement and imagination needs to remain clear. We know the planet is strongly irradiated. We know the dayside is hot. We know the nightside is thermally faint. We have strong evidence for synchronous rotation. We know a substantial atmosphere is absent or severely limited. From those facts, a fixed transition region follows naturally, but we do not know whether someone standing there would see a flat basaltic plain, a cratered landscape, fractured highlands, ancient lava flows, or some combination of all of them. There is no map, there is no surface image. Even the word line makes the place sound thinner than it really is from a thermal point of view. The geometric boundary may be exact, but the physically interesting region could extend far to either side. Travel inward from the Terminator and stellar heating increases gradually. Travel outward and direct light disappears, but the ground does not instantly forget the hot hemisphere nearby. Temperature, mineral behaviour, topography, and internal heat create a more complicated transition. Perhaps future phase curve measurements with Webb or later telescopes will constrain this region more closely. A full thermal map would require observing how infrared brightness changes throughout the orbit with enough precision to reconstruct different longitudes. Multiple wavelengths could help separate temperature effects from surface composition. Better measurements might show whether the hottest point lies exactly beneath Batsu. They could reveal whether the evening side and morning side equivalents are truly identical, even though there is no ordinary evening or morning. Any measurable asymmetry would be interesting. An atmosphere could shift heat. Different rock types could change thermal emission. Geological differences between hemispheres could alter how quickly the surface warms or radiates energy. Internal heating might create unexpected warm regions. At present, the broad phase curve is strikingly consistent with a dark, exposed, synchronously illuminated rocky world. That simplicity is valuable because it gives astronomers something close to a natural experiment. The star provides a permanent heat source on one side, the planet provides a permanent dark side, the Terminator sits between them. There is no thick atmosphere doing most of the thermal work. By measuring the radiation leaving different portions of Kuaꞌkua, researchers can test how bare planetary surfaces behave under conditions that cannot be reproduced on Earth at planetary scale, and the same boundary that helps us understand temperature also leads directly to another question. If almost no substantial air exists today, was Kuaꞌkua always this bare? That missing atmosphere is one of the most important clues Kuaꞌkua gives us, because a bare rocky world does not necessarily begin its life bare. Planets change. Young rocky planets can release gases from their interiors. They can receive volatile material through impacts. Some begin with envelopes of hydrogen and helium captured from the disk of gas surrounding their young star. Volcanoes can later add carbon dioxide, sulfur compounds, water vapor, and other gases to the surface environment. Earth has an atmosphere partly because gases were retained and recycled over geological time. Venus kept an atmosphere so massive that the pressure at its surface is more than 90 times the pressure at sea level on Earth. Mars went in another direction. It still has an atmosphere, but it is thin, and evidence preserved in rocks and ancient landscapes tells us that the planet once had conditions very different from those we see today. Kuaꞌkua appears to have gone farther still. As far as current observations can tell, there is no substantial atmosphere surrounding it now. The question is whether one was lost, whether one never became large in the first place, or whether several different processes worked together over billions of years. We do not yet know the exact history. That is worth saying clearly. There is no measurement showing us a photograph of Kuaꞌkua 3 billion years ago, with a thick atmosphere slowly blowing away into space. Astronomers have the planet we see today, measurements of its star, models of atmospheric escape, and information about how rocky planets behave under intense irradiation. From those pieces they can reconstruct plausible histories. The simplest place to begin is with Kuaꞌkua's orbit. The planet sits extremely close to Batsu, completing one revolution in just over 11 hours. That distance exposes it to far more stellar energy than Earth receives from the Sun. For rock, this creates the hot dayside we have already seen. For gas, the consequences can be even more serious. An atmosphere is held to a planet by gravity. Every molecule moves. The warmer the gas becomes, the faster its particles move on average. Most remain bound because their speeds are not high enough to escape the planet's gravitational pull. But the upper atmosphere is exposed to radiation from the star, including ultraviolet and X-ray radiation that can deposit energy high above the surface. Heat the upper atmosphere strongly enough, and it expands. In extreme cases, gas can flow outward in a large-scale escape process, rather than simply losing an occasional molecule. This can be particularly important when a planet is young. Young stars are often more active than older stars. M-dwarfs can spend long periods producing strong high-energy radiation, including ultraviolet and X-rays. That means a planet close to an M-dwarf may face its most difficult atmospheric conditions at exactly the time when its atmosphere is still evolving. Batsu is old today and rotates slowly. Recent estimates place its age at roughly 7.8 billion years, making it several billion years older than the solar system. It is relatively inactive now, but measurements with the Hubble Space Telescope have still detected ultraviolet activity, including a far ultraviolet flare. Those observations help scientists estimate the high-energy radiation environment that Kuaꞌkua experiences today. Its earlier environment may have been much more intense. That matters because atmospheric escape does not need to remove an atmosphere this weak. It has billions of years. A tiny loss rate maintained for a very long time can remove a large amount of material. Increase that loss rate during the active youth of the star. Place the planet extremely close to the radiation source, and the problem becomes much more severe. The lightest gases are the easiest to lose. Hydrogen is especially vulnerable. Suppose young Kuaꞌkua acquired a hydrogen and helium envelope while the planetary system was forming. Gas from the young disk could surround a growing rocky core. This happens naturally in planet formation models. Some rocky planets keep enough hydrogen and helium to become mini Neptunes. Others lose those light envelopes and are left as exposed rocky worlds. Kuaꞌkua's intense irradiation and present high density make a substantial surviving hydrogen-helium envelope very unlikely. Recent mass measurements put the planet at little over twice Earth's mass, with a radius around 1.29 times Earth's, giving it a density consistent with a predominantly rocky composition rather than a low-density world wrapped in a large gaseous envelope. So an early hydrogen atmosphere, if Kuaꞌkua ever had one, may have been temporary. High-energy radiation can drive what is called hydrodynamic escape. Instead of individual hydrogen atoms occasionally reaching escape speed, the upper atmosphere becomes hot and expanded enough for gas to flow outward. Hydrogen escaping in large quantities can sometimes drag heavier atoms along with it. A young planet can therefore lose more than just hydrogen. The atmosphere can be stripped and chemically altered while the star is still young. There is a useful comparison with Earth here. Earth also receives ultraviolet radiation. Our atmosphere also loses particles to space. The difference is the scale of the environment. Earth sits 1 astronomical unit from the Sun. Kuaꞌkua sits only a tiny fraction of an astronomical unit from Batsu. Even though Batsu is much less luminous than the Sun, Kuaꞌkua is so close that the planet receives intense irradiation. Moving a world inward changes the problem dramatically. You could think of gravity as the planet trying to hold onto a blanket while the star spends billions of years pulling threads from it. A heavy blanket is harder to remove. A light one is easier. Unfortunately for a young rocky planet, hydrogen is about as light as atmospheric material gets. But removing a primordial hydrogen envelope does not necessarily leave a rocky planet permanently airless. This is where the story becomes more complicated. Rocky planets can build secondary atmospheres. A secondary atmosphere is made from gases released or delivered after the original hydrogen-rich envelope has been lost. Volcanoes are one major source. A planet's interior can contain volatile compounds. As rock melts and magma rises, gases dissolved in the magma can escape at the surface. Earth's volcanic gases include water vapor, carbon dioxide, sulfur dioxide, and other compounds. Early Earth probably built much of its atmosphere through processes that included interior outgassing. Venus also appears to have accumulated a thick secondary atmosphere. So even if Kuaꞌkua lost an early hydrogen envelope, its interior might have tried to build another atmosphere later. If that happened, something prevented the new atmosphere from becoming substantial, or surviving until today. In 2019, Spitzer observations gave the first strong evidence for this. The thermal phase curve showed a very hot dayside and an extremely faint nightside. A thick atmosphere would carry heat from one hemisphere to the other. The observed temperature contrast was so large that atmospheres with surface pressures above about 10 bars were ruled out by the analysis, while thinner atmospheres were considered vulnerable to long-term erosion by the stellar wind. 10 bars is a substantial atmosphere. Earth's average surface pressure is about 1 bar. A 10-bar atmosphere would be roughly 10 times that pressure at the surface, although the exact amount of atmospheric mass depends on gravity and composition. Spitzer was therefore telling astronomers that Kuaꞌkua was not hiding beneath a Venus-like blanket. The day-night temperature difference was far too strong. But there was still room for something thinner. A tenuous atmosphere can move much less heat than a thick one. Spitzer alone could not exclude every possible gas layer at every pressure and composition. That is where Webb became important. The James Webb Space Telescope measured Kuaꞌkua's thermal spectrum from about 5 to 12 micrometers. Those wavelengths carry information not only about the surface, but also about gases that might absorb and emit infrared radiation above it. The 2026 analysis placed a strong upper limit on carbon dioxide, disfavoring concentrations corresponding to pressures of about 100 millibars or more in the tested models. For sulfur dioxide, the limit was much smaller, around 10 microbars. The measurements found no evidence for an accumulated atmosphere of volcanic gases. 100 millibars is about 1/10 of Earth's sea level atmospheric pressure, so the question is no longer merely whether Kuaꞌkua lacks a thick 10-bar atmosphere. For important gases such as carbon dioxide and sulfur dioxide, Webb pushes the allowed amounts much lower. The exposed rock is becoming increasingly difficult to hide behind any conventional atmosphere. That gives us an interesting problem. Kuaꞌkua is rocky. Rocky planets can outgas. The system is old. Yet a large volcanic atmosphere has not accumulated. There are several possible reasons. The first is that gases were produced and then removed. High-energy radiation is one way, stellar wind is another. A stellar wind is a flow of charged particles leaving a star. The Sun produces one, and Earth is continuously immersed in it. Our magnetic field redirects much of the incoming charged material around the planet, creating a magnetosphere. Some particles still interact with our upper atmosphere, especially near the poles, producing auroras and contributing to atmospheric escape. M-dwarfs can create difficult stellar wind environments for close planets. Kuaꞌkua is extremely close to Batsu. If the planet lacks a strong protective magnetic field, its upper atmosphere could interact directly with charged particles from the star. Even with a magnetic field, the situation is complicated. A magnetic field does not simply place a perfect shield around a planet and end atmospheric loss. The strength of the field, structure of the stellar wind, ionization of the upper atmosphere, and many other factors determine what happens. We do not currently know whether Kuaꞌkua has a global magnetic field. There is no distant instrument capable of simply pointing at the planet and measuring its magnetic poles. So it would be a mistake to say the planet lost its atmosphere, because it had no magnetosphere. That is one possibility among several, not an observed fact. What we do know is that the 2019 atmospheric analysis specifically found thinner atmospheres vulnerable to erosion from stellar wind under plausible conditions. That erosion has had billions of years to operate. Another possibility is that Kuaꞌkua simply does not outgas very efficiently today. Planetary interiors cool. A rocky planet can begin with extensive melting and vigorous volcanism, then gradually become less active. Earth remains geologically active because it has a large interior containing heat left from formation and radioactive decay. Its mantle convects, its plates move. Magma reaches the surface. The moon, being smaller, cooled more quickly and lost most of the large-scale volcanism that once covered its maria with lava. Kuaꞌkua is more massive than Earth, so size alone would not make it an obvious candidate for rapid cooling. But geological activity depends on much more than size. Composition matters. Interior structure matters. Tidal heating matters. The history of melting matters. Whether a rigid lid forms matters. The distribution of radioactive elements matters. We do not know enough about Kuaꞌkua's interior to reconstruct all of this confidently. Recent mass and radius measurements indicate a dry, rocky interior, with one 2026 analysis finding that only trace amounts of bulk water are permitted by its interior models. That does not tell us exactly how much gas the mantle can release today, but it supports the broader picture of a dry terrestrial planet rather than a volatile rich world. Webb's lack of accumulated carbon dioxide and sulfur dioxide may therefore have more than one explanation. Maybe volcanic outgassing is weak, maybe gases emerge but escape, maybe strong volcanism ended long ago, maybe early atmospheric loss removed volatile reservoirs so effectively that later volcanism had relatively little left to release. The observations do not yet choose cleanly among all of those histories, and there is another possible problem for atmospheric survival: the nightside. Suppose Kuaꞌkua somehow produced a thin secondary atmosphere. Gas heated on the dayside would move toward the cooler nightside. As it cooled, some atmospheric species could condense. Under suitable temperature and pressure conditions, carbon dioxide or other substances can freeze onto the ground. This is called atmospheric collapse, when enough of the gas condenses that the atmosphere itself becomes greatly reduced. Tidally locked planets are especially interesting in this context because the nightside never receives direct stellar heating. A sufficiently thin atmosphere may struggle to keep its dark hemisphere warm. The colder the nightside becomes, the easier it may be for some gases to condense there. The more gas condenses, the thinner the atmosphere becomes. The thinner the atmosphere becomes, the worse it becomes at transporting heat. That can create an awkward feedback. This does not prove that Kuaꞌkua's atmosphere froze onto its nightside. We have no measurement showing enormous carbon dioxide ice caps sitting in permanent darkness. Given the planet's extreme irradiation and long escape history, much of the atmosphere may simply have been lost to space. Still, nightside condensation is one of the processes scientists consider when studying thin atmospheres on tidally locked worlds. The atmosphere has to survive both the hot hemisphere and the cold one. On one side, radiation encourages heating, chemistry, and escape. On the other, low temperatures can encourage condensation. Kuaꞌkua has spent billions of years caught between those extremes. impacts add another complication. Early planetary systems were messy. Large objects collided. Some impacts delivered volatile material. Others removed it. A sufficiently energetic collision can blow part of an atmosphere into space. Repeated impacts can change atmospheric mass in either direction, depending on the size, speed, angle, and composition of the objects involved. We have no impact history for Kuaꞌkwa. Its surface may preserve craters, but we cannot resolve them. So impacts remain another plausible contributor rather than a demonstrated cause. The planet's location may also tell us something about what materials were available when it formed. Close to a young star, temperatures in the planet-forming disk can be high. Volatile substances such as water are harder to incorporate into growing rocky bodies there than farther out. If Kuaꞌkwa formed near its present orbit, it may have started relatively dry. If it formed farther away and migrated inward, its original composition could have been different. We do not yet know which history applies. This means the missing atmosphere may not have one dramatic explanation. There may never have been a moment when Kuaꞌkwa possessed a thick Earth-like atmosphere and suddenly lost it. Instead, imagine several processes operating in sequence. A young rocky planet forms. Perhaps it begins with a light hydrogen-rich envelope. The young red dwarf produces intense high-energy radiation. The light envelope escapes. The interior releases heavier gases. Some are removed by stellar radiation and charged particles. Some may condense on the dark hemisphere. Large impacts rearrange the surface and alter the atmosphere. Volcanism declines or becomes intermittent. The star gradually becomes quieter. Billions of years later, astronomers arrive with Spitzer and Webb and find a dark, rocky surface with very little gas remaining above it. That sequence is plausible. It is not a recorded history. The distinction matters because science is often strongest when it tells us what remains uncertain. Kuaꞌkwa does not come with geological records that we can collect and date in a laboratory. There are no ancient sedimentary rocks available to show us where the rain once fell. No trapped bubbles in minerals reveal the composition of an early atmosphere. No spacecraft has measured ions flowing away from the planet today. We are reconstructing a history from the conditions that survived. One of the most important surviving clues is the surface itself. If Kuaꞌkwa had possessed a thick atmosphere for most of its history, that atmosphere could have altered the ground. Weathering would change minerals. Volcanic gases could react with surface materials. Pressure and temperature would affect which compounds remained stable. A planet with liquid water would undergo even more dramatic chemical change. Instead, Webb sees an old, dark surface consistent with basalt or other olivine-rich material that has been exposed to space weathering. The lack of accumulated volcanic gases fits that same general picture. The surface looks old and exposed rather than hidden beneath an active atmosphere. Space weathering then becomes part of the atmosphere story. Without a substantial layer of gas, the ground receives direct exposure to energetic particles and micrometeorite impacts. The uppermost minerals change. Fresh material gradually becomes altered. On the Moon, these processes can darken and chemically modify surface grains. Kuaꞌkwa lives far closer to its star than the Moon does to the Sun, so its exposure environment is different and potentially much more intense. A bare surface is not merely evidence that air is missing. It also begins recording what happens after the air is gone. That gives astronomers another way to think about the planet. The atmosphere may have vanished, but it left consequences behind. The hot dayside tells us that heat is not being redistributed efficiently. The cold nightside tells us the same thing from the opposite direction. The old dark rock tells us that the surface has spent considerable time exposed. The lack of carbon dioxide and sulfur dioxide tells us that volcanic gases have not built up into a detectable substantial atmosphere today. The planet's mass and density tell us that it is a rocky world rather than a small gas-rich planet. The high-energy spectrum of Batsu tells us that even an old, relatively quiet red dwarf still produces ultraviolet radiation and occasional flaring. Each piece removes another possibility. Eventually, the broad picture becomes difficult to avoid. Kuaꞌkwa is a rocky planet that has not managed to keep much air. Whether it lost most of that air early or continued losing it gradually is still uncertain, and there is an important lesson here for planets around red dwarfs in general. Red dwarfs are the most common stars in the galaxy. They are also attractive places to search for small planets, because their size makes planetary transits easier to detect. A rocky planet crossing a small star blocks a larger fraction of the star's light than the same planet crossing something as large as the Sun. Their low luminosity also places their temperate regions relatively close to the star, producing short orbital periods and frequent transits. That makes them excellent targets for observation. But the same close orbits that make these planets easier to find can make atmospheric survival more difficult. A planet can sit at a temperature where liquid water might seem possible, based only on ordinary stellar heating, and still face high-energy radiation, flares, stellar wind, tidal locking, and atmospheric escape. Kuaꞌkwa itself is much too hot to be a temperate example, but it allows astronomers to test the extreme end of the problem. Here is a rocky planet around an M-dwarf. It sits very close to the star. Its atmosphere is essentially absent. Its surface is directly visible in thermal radiation. The environment has had billions of years to reach this state. Understanding how it got there helps researchers ask better questions about worlds farther from their stars. How far away does a rocky planet need to be before atmospheric retention becomes easier? How massive does it need to be? How much does stellar activity matter? Can volcanic outgassing replace gases as quickly as they are lost? Do magnetic fields help enough to change the outcome? Can some M-dwarf planets keep thick atmospheres while their neighbours become bare rock? There is no single rule saying that every planet around a red dwarf must lose its air. We already know planetary outcomes depend strongly on orbital distance, mass, composition, stellar history, and the atmosphere itself. Kuaꞌkwa gives us one particularly exposed example, not a universal template. Even on this one world, the exact sequence remains incomplete. Perhaps a hydrogen envelope disappeared first. Perhaps a secondary atmosphere followed. Perhaps a thin layer of gas still exists today below current detection limits. When astronomers say that Kuaꞌkwa has no atmosphere, the careful version is that there is no evidence for a substantial atmosphere, and current observations place strong limits on several plausible atmospheric compositions. Science generally leaves the door open a few millimeters. A surface-bound exosphere containing tiny amounts of material would not behave like an atmosphere in the Earth-like sense. Atoms could be knocked from the ground by radiation or impacts. Volcanic events could release brief local gases. Material could exist at pressures far below the limits of current observations. None of that would provide the heat transport, weather, or pressure associated with a substantial atmosphere. So Kuaꞌkwa may not be perfectly empty above its rocks. It is simply extraordinarily bare. Almost everything we have learned about Kuaꞌkwa has arrived in the form of light. There are no photographs of its surface showing individual craters. No spacecraft has flown past it. No lander has placed an instrument on the ground. We have never seen a mountain there, collected a rock sample, or watched Batsu hanging above the permanent dayside. Kuaꞌkwa is about 49 light-years away, and even our most powerful telescopes cannot resolve its surface into a detailed globe. Yet astronomers can still ask what the ground may be made of. That sounds almost unreasonable at first. A planet more than 12,000 kilometers across is orbiting a small star hundreds of trillions of kilometers away. And from Earth, the two appear so close together that we cannot simply separate the planet from the star in an ordinary image. The star overwhelms the planet in visible light. Kuaꞌkwa itself contributes only a tiny fraction of the radiation reaching our telescopes. And somehow, from that tiny contribution, researchers are beginning to distinguish between different kinds of rock. The process begins with a useful fact about matter. Different materials interact with light differently. Some wavelengths are absorbed strongly, others are reflected. Hot materials emit thermal radiation, and the strength of that emission changes with wavelength depending on temperature, composition, texture, and other physical properties. A piece of basalt does not produce exactly the same infrared spectrum as a piece of granite. Fine mineral powder can behave differently from solid rock. A freshly exposed surface can differ from one that has spent millions or billions of years being struck by radiation and tiny impacts. If you can measure those differences accurately enough, the light becomes information about the material that produced it. This is spectroscopy. On Earth, spectroscopy is used everywhere, from chemistry laboratories to astronomy. A scientist can place a sample in an instrument, shine light on it, and measure how the sample responds across different wavelengths. Instead of treating light as one combined brightness, the instrument separates it into many parts. Visible light through a prism gives the familiar rainbow. Infrared spectroscopy does something similar at wavelengths our eyes cannot see. The result is a spectrum. A spectrum can contain broad slopes, peaks, dips, and features associated with particular molecules or minerals. Astronomers then compare an unknown spectrum with measurements and models of known substances. Kuaꞌkua offers an unusual opportunity because its surface is extremely hot. The planet does not need to reflect enough visible starlight for us to study the ground. It emits its own thermal radiation. Every object with a temperature above absolute zero emits radiation. Your body does. The walls around you do. Your pillow is quietly producing infrared radiation right now, although this is probably the least dramatic thing your pillow has done all day. Most objects at ordinary room temperature emit primarily at infrared wavelengths. Heat them, and their radiation becomes stronger and shifts towards shorter wavelengths. Kuaꞌkua's dayside is near 1,000 Kelvin, making its thermal emission much easier to detect than that of a cooler Earth-like surface. This heat is one of the reasons such an inhospitable planet is scientifically convenient. A cooler, rocky world would be harder to measure. Kuaꞌkua is essentially providing its own infrared signal. The difficulty is separating that signal from Batsu. One method uses the planet's orbit. Kuaꞌkua passes in front of its star from our point of view. That is the transit that originally revealed the planet. During the transit, the system becomes slightly dimmer because Kuaꞌkua blocks part of Batsu. The amount of blocked light tells astronomers about the planet's size relative to the star. NASA's exoplanet archive currently lists Kuaꞌkua at about 1.29 Earth radii, with an orbital period of about 0.463 days. Half an orbit later, something equally useful happens. Kuaꞌkua moves behind Batsu. This is called a secondary eclipse or occultation. Immediately before the planet disappears, the telescope receives radiation from both objects. There is the much larger signal from Batsu, plus a small amount of thermal emission from Kuaꞌkua's hot dayside. Then the planet moves behind the star. Its contribution disappears. For a short time, the telescope sees Batsu without the planet's dayside emission. Measure the brightness before the eclipse. Measure it during the eclipse. Compare the two. The difference is the radiation that had been coming from Kuaꞌkua. The planet is effectively measured by temporarily removing it from the observation. It is a clever technique because nobody needs to resolve the two objects spatially. The star does the hiding for us. The challenge is that the difference is tiny. Imagine trying to determine how warm a candle is while it sits beside a powerful lamp, then having someone briefly place the candle behind the lamp. You would need an extremely stable instrument to notice the missing heat. Now place the lamp 49 light-years away and make the candle a rocky planet. This is why instruments such as Spitzer and Webb matter. Spitzer approached Kuaꞌkua by watching the system throughout the planet's orbit. Instead of measuring only a single eclipse, astronomers observed how the combined infrared brightness changed as different portions of the planet's surface were oriented toward us. This produced the thermal phase curve. As the hot dayside became more visible, the measured infrared brightness increased. When the cold nightside faced us, it decreased. The change was large and approximately symmetric. The dayside brightness temperature at 4.5 micrometers was measured at about 1040 Kelvin, while the nightside signal was consistent with 0 at that wavelength within the observational uncertainty. The data were well matched by a bare rock planet with a low bond albedo, below about 0.2 in the published analysis, and atmospheres above roughly 10 bars were ruled out. That result was important because it turned the surface into the leading explanation for the infrared emission. If Kuaꞌkua had been wrapped in a thick atmosphere, the phase curve would have looked different. Air would carry heat toward the night side. Atmospheric molecules would absorb and emit radiation. Clouds could reflect stellar energy. The location and shape of the hottest region might shift. Instead, the planet behaved much more like exposed rock directly heated by Batsu. Spitzer could tell us that the surface was dark and that the heat was concentrated on the day side. It could not tell us in detail what minerals were sitting there. For that, astronomers needed a broader spectrum. The James Webb Space Telescope provided it. Webb carries the mid-infrared instrument, usually called MIRI. MIR is designed to detect infrared wavelengths where relatively cool objects, including planets, dust, and distant galaxies, can emit strongly. For Kuaꞌkua, astronomers used MIRI to measure thermal radiation across roughly 5 to 12 micrometers. Instead of receiving one infrared brightness value, they could see how the planet's emission changed across a range of wavelengths. That difference is crucial. A single measurement can tell you that something is bright or faint. A spectrum begins to tell you why. Webb observed several secondary eclipses. Each time Kuaꞌkua approached the far side of Batsu, the telescope measured the star and planet together. The planet vanished. The signal dropped slightly. Then Kuaꞌkua reappeared. Repeating this process allowed researchers to improve the precision and reduce the chance that instrumental noise or stellar variability would be mistaken for planetary information. The extracted planetary spectrum was then compared with models and laboratory spectra for different surface materials. The result published in May 2026 was surprisingly restrained. The spectrum was dark and relatively featureless. That might sound disappointing. Astronomers generally enjoy features because features provide obvious clues. A sharp absorption band can point toward a particular gas. A strong mineral feature can narrow the surface composition. A mostly smooth spectrum forces more careful comparison. But featureless does not mean useless. The overall brightness, shape, and absence of expected features can eliminate possibilities. The best matches for Kuaꞌkua were dark, low silica surfaces, especially materials such as basalt and other olivine-rich rocks. Fresh, bright, silica-rich surface types were poor matches. Fine, fresh powders were also inconsistent with the spectrum unless processes such as space weathering had changed their appearance. Basalt is a useful word here because it gives us something familiar to compare with. Basalt forms from relatively low silica magma. It is common on Earth. Most of Earth's oceanic crust is basaltic. Walk across a young lava field in Hawaii or Iceland, and much of the dark rock beneath you will be basalt. The Moon contains enormous basaltic plains created by ancient volcanic eruptions. Mars has extensive basaltic terrain, so the material suggested for Kuaꞌkua is not some exotic substance requiring an entirely new chemistry. It belongs to the family of rocks that rocky planets naturally produce. What differs is the environment. Kuaꞌkua's basalt-like surface has probably spent a very long time without rain, oceans, plants, soil chemistry, or a thick atmosphere. It is heated continuously on one hemisphere. It receives energetic radiation. Micrometeorites strike it without being slowed by a substantial atmosphere. Its surface may therefore look and behave differently from freshly cooled basalt on Earth. The Webb analysis also allowed researchers to consider olivine-rich material. Olivine is a silicate mineral rich in magnesium and iron. It is abundant in Earth's upper mantle and appears in meteorites and other planetary materials. If a planet exposes material derived from its mantle, perhaps through extensive volcanism, impacts, or a particular history of crust formation, an olivine-rich surface becomes plausible. Again, This does not mean astronomers have identified a field of green olivine crystals on Kuaꞌkua. The planet is unresolved. The spectrum represents radiation averaged across a huge fraction of its dayside. What the data say is that dark, low-silica materials such as basalt and olivine-rich rock reproduce the observations better than many alternatives. There is an important distinction between composition and appearance. A mineral that looks one way in a clean laboratory sample may look different after long exposure to space. On an airless world, energetic particles can alter the surface. Tiny meteorite impacts can melt microscopic portions of rock. Fresh material becomes fractured. Chemical and structural changes occur in the uppermost grains. These processes are grouped under the term space weathering. We know space weathering well from the Moon. Apollo astronauts returned lunar samples that scientists could compare with remotely observed lunar terrain. Older exposed material often looks darker and has different spectral properties from freshly excavated rock. Mercury is also heavily space-weathered. Asteroids show similar effects. Kuaꞌkua may have experienced this kind of processing for billions of years under conditions far more intense than those on the Moon. The 2026 Webb analysis found that an old space-weathered surface fits the observations well. Fresh small grains are too bright in the relevant spectral comparisons, but weathering can darken powders and make them more compatible with the data. That gives the apparently simple phrase, dark surface, a long history. The ground may be dark because of what it is made from. It may also be dark because of what has happened to it. Separating those two effects is difficult. Suppose you measure a low reflectivity. That could indicate naturally dark minerals, or it could indicate brighter material altered by radiation. Texture matters too. A solid slab behaves differently from gravel. Gravel behaves differently from fine dust. Grain size changes how photons interact with the surface. Porosity matters. Roughness matters. Temperature matters. You begin by asking, what is the planet made of? And soon discover that the answer depends partly on whether the material is a smooth rock, a pile of rubble, or dust that has spent several billion years being repeatedly struck by particles from a red dwarf. Planetary geology rarely allows a one-word answer. The researchers compared Kuaꞌkua's spectrum with laboratory measurements of rocks and minerals. This is one of the quieter links between studying Earth and studying exoplanets. A rock sitting in a laboratory can help interpret radiation from a planet 49 light-years away. Scientists measure how basalt, olivine and other materials reflect or emit infrared radiation. They build spectral libraries. Those libraries become reference collections. When Webb obtains an unknown planetary spectrum, researchers can ask which known materials produce something similar under appropriate temperatures and textures. It is a little like identifying a song from a few notes, except the notes are infrared wavelengths and the singer is a super-Earth. There is uncertainty, of course. Different materials can resemble one another. Mixtures can produce spectra different from pure minerals. The surface may contain several rock types at once. One region could be basaltic, while another exposes something else. Webb sees a combined signal. If half the visible hemisphere is one material and half another, the resulting spectrum may blend their characteristics. This means Kuaꞌkua is not proven to be covered from pole to pole in a single type of basalt. The measurement gives us the dominant properties of the emitting surface. The strongest conclusion is broader. The dayside is dark. The composition is consistent with low silica rock. Basaltic or olivine-rich materials fit well. Bright silica-rich surfaces resembling evolved continental crust on Earth do not. That last point is especially interesting. Earth's continents contain abundant granite and related rocks that are relatively rich in silica. Granite is part of a crust that has been repeatedly processed through melting, differentiation, tectonics, and interactions with water. It is not simply what every rocky planet naturally produces on its surface. Kuaꞌkua appears to remind us of that. A planet can be rocky without having anything resembling Earth's continental crust. No oceans are required. No continents are required, no plate tectonics are required. Rocky planet describes a broad family, not an Earth costume available in several sizes. The absence of a substantial atmosphere helps researchers study this geology more directly. Webb also tested whether atmospheric gases could be contributing to the infrared spectrum. Carbon dioxide and sulfur dioxide were particularly important because both can be associated with rocky planet atmospheres and volcanic outgassing. The 2026 study found no evidence of accumulated volcanic gases and placed strong upper limits on both, about 100 millibars for carbon dioxide at the reported 5 sigma constraint, and about 10 microbars for sulfur dioxide at 3 sigma. That strengthens the bare surface interpretation. A thick atmosphere is not producing the observed spectrum. A large volcanic gas layer has not collected above the planet. The rock itself is doing most of the talking. This also gives a clue about geological activity. If Kuaꞌkua were undergoing vigorous continuous volcanism that released large quantities of gas faster than the star could remove them, we might expect some detectable atmospheric buildup. We do not see that. The Max Planck Institute team involved in the analysis therefore noted that the results are consistent with prolonged geological inactivity, though the observations cannot prove that every volcanic process on Kuaꞌkua has stopped. There could still be occasional eruptions. There could be magma beneath the surface. Ancient volcanism may have created much of the basalt we see. What is missing is evidence for enough current outgassing to produce a substantial atmosphere. The ground may therefore be recording an older geological era. Perhaps broad lava flows cooled long ago. Perhaps impacts exposed mantle-rich material. Perhaps an early crust was replaced by volcanic resurfacing. Perhaps intense stellar conditions stripped gases while leaving dark volcanic rock behind. Each possibility would produce a somewhat different geological history. At present, Webb cannot choose every step of that history. It can tell us that some stories fit the evidence better than others. A planet with a thick carbon dioxide atmosphere does not fit well. A bright silica-rich crust does not fit well. A dark exposed basaltic surface fits much better. That is already a remarkable narrowing of possibilities for a world we cannot see as anything more than a tiny contribution to a star's light. The older Spitzer measurement and the newer Webb spectrum complement each other nicely. Spitzer told us how the planet's heat changes around the orbit. It revealed the large day-night contrast and suggested an atmosphere-free dark surface. Webb divided the dayside thermal radiation into wavelengths and asked what kind of surface could actually create it. One instrument established the broad thermal behavior. The other began investigating the geology. Together, they turned Kuaꞌkua from a radius and an orbital period into something much more physically specific. We can say it is larger than Earth. We can say it circles an old M dwarf every 11 hours. We can say it is very likely tidally locked. We can say the dayside is extremely hot. We can say the nightside receives very little redistributed heat. We can say there is no evidence for a substantial atmosphere. And now we can say the exposed surface appears dark, low in silica, and compatible with basaltic or olivine-rich rock that has probably been altered by long-term space weathering. None of those facts required a spacecraft to travel there. They came from transits, eclipses, phase curves, spectra, laboratory rocks, and careful models. That is the part of the story that may matter well beyond Kuaꞌkua itself. For years, exoplanet astronomy was largely about discovery. Find a dip in starlight, measure the period, estimate the radius, add another world to the catalogue. Then came mass measurements, atmospheric searches, temperature maps, and increasingly precise spectra. Now a telescope is beginning to ask what the exposed crust of a rocky exoplanet might be made from. Kuaꞌkua is useful not because basalt itself is surprising, but because we can detect evidence for basalt at all. The techniques being tested on this hot, conveniently observable world can be applied to other rocky planets. Some will have atmospheres, some will not. Some may expose surfaces dominated by different minerals. Others may be hotter, cooler, younger, more volcanic, or more heavily weathered. As more of them are measured, Kuaꞌkua stops being merely an unusual planet and becomes one point in a much larger comparison. That larger comparison is where Kuaꞌkua becomes more useful than its extreme conditions might first suggest. Nobody studies this planet because it looks like a good second Earth. It does not. Its 11-hour orbit, intense stellar heating, permanent dayside, permanent nightside, and apparent lack of a substantial atmosphere place it far from the conditions humans normally associate with a habitable world. But habitability is only one question in planetary science. Before we can understand which rocky planets might support familiar environments, we need to understand rocky planets themselves. How do they form? How do they lose atmospheres? How quickly do their interiors cool? What kinds of crust do they produce? How does a nearby star reshape them? What happens when a planet is tidally locked for billions of years? How do bare surfaces change under constant radiation? And how can we tell the difference between all those possibilities from dozens of light years away? Kuaꞌkua gives researchers a place to test those questions under unusually clear conditions. Its lack of a thick atmosphere is scientifically inconvenient in one sense, and extremely useful in another. There are few clouds, gases, or weather systems hiding the surface signal. Heat from the dayside escapes directly into space. The night side remains faint. The thermal pattern closely follows stellar heating. The exposed ground produces a spectrum that Webb can measure. This makes Kuaꞌkua something like a calibration case for rocky exoplanets. If astronomers understand what a bare, hot, tidally locked planet looks like in infrared light, they become better at recognizing when another planet does not look bare. That distinction will matter increasingly as more small worlds are observed. Imagine two rocky planets with similar sizes and similar stellar heating. The first shows a very hot dayside and a nearly undetectable nightside. The second shows a cooler dayside and a warmer nightside. The difference may indicate that the second planet has something moving heat around. A substantial atmosphere would be one possibility. A thick atmosphere absorbs energy, circulates it through winds, and carries part of it into darkness. The thermal phase curve becomes less extreme. This is why Kuaꞌkua's Spitzer observations were so important. They provided an example of what poor heat redistribution looks like on a rocky exoplanet. The large phase curve amplitude and the dayside temperature near 1040 Kelvin were well fit by a bare dark surface, while thick atmospheres above about 10 bars were ruled out. That measurement gave astronomers a reference point. Then Webb began examining other rocky worlds. The results have already shown that there is no single rule applying to every close-in terrestrial planet. TRAPPIST-1b, for example, is approximately Earth-sized and orbits a cool red dwarf. Webb measurements of its thermal emission have been most consistent with little or no atmosphere capable of redistributing heat. TRAPPIST-1c also lacks a thick carbon dioxide-rich atmosphere, although thinner atmospheric possibilities have been harder to eliminate completely. More recent 2026 phase curve work on the two innermost TRAPPIST-1 planets continues to rule out thick atmospheres for both, with TRAPPIST-1b appearing particularly airless. Then consider 55 Cancri e. This is also a very hot rocky exoplanet on an extremely short orbit. For years, astronomers debated whether it had an atmosphere at all. Webb observations published in 2024 indicated something very different from Kuaꞌkua: a substantial secondary atmosphere, probably rich in carbon dioxide or carbon monoxide and potentially supplied by a magma ocean. That contrast matters. Hot rocky planets do not all follow the same path. One may become a bare, dark surface. Another may maintain or replenish an atmosphere despite enormous stellar heating. A third may sit somewhere between the two, with a thin atmosphere that appears and disappears, depending on volcanic activity, escape, or condensation. The simple categories we learned from our own solar system are not enough. Mercury is nearly airless. Venus has an enormous atmosphere. Earth has a moderate atmosphere and oceans. Mars has a thin atmosphere. Those 4 worlds already demonstrate remarkable diversity, despite forming around the same star from related material. Move to other stars, change the orbital distance, planetary mass, formation history, stellar activity, and age, and the range of possible outcomes becomes even larger. Kuaꞌkua adds a particularly extreme point to that collection. It tells us that a rocky planet somewhat larger than Earth can spend billions of years close to an M-dwarf and end up with little detectable atmosphere. That is important when we think about planets around red dwarfs, because red dwarfs are common. They are small, cool, faint stars. Their low luminosity means that planets receiving moderate amounts of stellar energy must orbit much closer than Earth does around the Sun. Close orbits have observational advantages. A planet transits frequently. The transit blocks a relatively large fraction of a small star. The planet-star contrast in thermal emission can be more favourable than it would be around a Sun-like star. Those are some of the reasons many of our best opportunities for studying small exoplanets involve M-dwarfs. The same close orbits also create physical problems. Tidal locking becomes more likely. High-energy stellar radiation can strongly affect the atmosphere. Young dwarfs can remain active for long periods. Stellar winds interact with nearby planets. The habitable zone may be close enough that these effects remain important even for worlds receiving much less total energy than Kuaꞌkua. That does not mean planets around red dwarfs are automatically sterile or airless. Kuaꞌkua cannot answer that. It is far too hot and too close to Batsu to represent every M-dwarf planet. What it can do is help researchers test atmospheric loss models at the extreme end. If models predict that a world with Kuaꞌkua's size, orbit and irradiation should struggle to retain an atmosphere, observations can check the prediction. In this case, the observed planet is indeed nearly bare. That gives researchers more confidence in some parts of the physical framework while showing them where more detail is needed. A good model must not only explain why Kuaꞌkua has very little atmosphere, it should also explain why another intensely irradiated rocky planet, such as 55 Cancri E, may still possess one. That is harder, and therefore more useful. Maybe the planets began with different volatile inventories. Maybe their masses make escape rates different. Maybe one continually replenishes gas through volcanism. Maybe their stars produce different histories of ultraviolet and X-ray radiation. Maybe magma oceans store and release gases differently. Maybe magnetic environments matter. Probably several effects interact. With one planet you can tell a plausible story. With dozens, the stories have to agree with a pattern. That is why planetary populations are so important. Eventually, astronomers want to move from saying, "This planet appears to be airless," to saying something like, "Rocky planets of this size receiving this amount of radiation from stars of this type usually lose their atmospheres, except under these conditions." We are not there yet. Kuaꞌkua is one of the worlds helping us move in that direction. Its surface composition adds another dimension to the comparison. Until recently, measuring the physical nature of a rocky exoplanet usually meant determining its radius and, where possible, its mass. Radius tells us size. Mass combined with radius gives average density. Density helps distinguish a rocky planet from a low-density, gas-rich world. That is extremely useful, but average density cannot tell you what is actually exposed at the surface. Earth and Venus have similar sizes and broadly rocky bulk compositions. Stand on their surfaces, however, and you will notice one or two differences, preferably through instruments, in Venus's case. Surface mineralogy gives information about geological processing. Basalt can suggest mantle-derived volcanism. Silica-rich crust can indicate more extensive differentiation. Fresh powder can suggest a different surface history from ancient weathered rock. Volcanic gases can reveal ongoing interior activity. By combining density, atmospheric constraints, and surface spectra, astronomers begin connecting the outside of an exoplanet with its interior history. Kuaꞌkua's Webb spectrum favours dark, low silica material such as basalt or other olivine-rich rock, and fits an old space-weathered surface with no evidence of accumulated volcanic gases. That tells us something about what a rocky super-Earth does not necessarily become. Larger than Earth does not mean more Earth-like. A planet can be around 1.3 Earth radii and still lack continents, oceans, weather, and a substantial atmosphere. The term super-Earth can be misleading for exactly this reason. It refers mainly to size or mass. It does not mean an improved Earth. There is no guarantee of forests, pleasant beaches, or slightly more spacious houses. Some super-Earths may be ocean worlds. Some may have massive atmospheres. Some may have lava oceans. Some may resemble oversized Mercury-like objects. Kuaꞌkua appears to belong closer to that last category, although its permanent hemispheric heating makes even Mercury a limited comparison. The surface result also matters for future telescopes, because it demonstrates that rocky exoplanet geology is becoming observational rather than purely theoretical. Scientists have predicted exoplanet surface spectra for years. They calculated how basalt, granite, ultramafic rock, iron oxides, and other materials might appear. They built laboratory databases. They modelled space weathering. They asked whether Webb would have enough sensitivity to distinguish any of these possibilities. Kuaꞌkua is now providing a real test. The 2026 Nature Astronomy study explicitly describes Webb as opening direct characterization of rocky exoplanet surfaces through mid-infrared spectroscopy, because mineral spectral features can constrain chemistry, surface texture, geological history, and interior processes. This is still difficult work. Kuaꞌkua is unusually favourable because it is nearby by astronomical standards, hot, large enough to produce a measurable signal, and nearly atmosphere-free. A cooler Earth-sized planet with clouds would be much harder. The star may be active, the planetary signal may be weaker. Several geological surfaces can produce similar spectra. Atmospheres can obscure the ground. Instrumental noise matters. Even the star's own spectrum must be modelled precisely. So we should not imagine Webb producing geological maps of hundreds of Earth-like planets next year. What Kuaꞌkua shows is that the basic measurement can work. That changes what becomes worth attempting. Once a technique has succeeded on one favourable target, astronomers can ask where else it can be pushed. A slightly cooler planet, a smaller one, a different star, a surface with stronger mineral features, a planet where atmospheric and surface signals both contribute. Perhaps eventually several objects of similar size but different ages. Then geology outside the solar system begins turning into comparative geology. That is a major change. For centuries, every rock humans studied came from the solar system, mostly Earth. A few came from the Moon through Apollo and robotic missions. Meteorites provide samples from asteroids, Mars, and other bodies. Spacecraft have remotely studied Mercury, Venus, Mars, moons, asteroids, and comets. But all of those objects formed in our local neighbourhood from one protoplanetary disk surrounding the young Sun. Exoplanets formed around different stars. Their disks had different chemical compositions. Their stars have different masses and radiation histories. Their planetary systems evolved differently. Finding geological diversity among them would tell us whether the rocky bodies in our solar system are typical or unusual. Perhaps basaltic surfaces like Kuaꞌkua's will prove extremely common. That would make sense because basaltic volcanism appears naturally on many differentiated rocky bodies. Perhaps silica-rich crusts will be rare. That could tell us that Earth's continental geology requires a special sequence of processes. Maybe water is important. Maybe plate tectonics is important. Maybe repeated crustal recycling is required. We cannot answer those questions from Kuaꞌkua alone, but its spectrum gives us the first kind of measurement needed to ask them observationally. Atmospheric survival can be studied in the same comparative way. Consider a future collection of rocky planets around red dwarfs. For each one, astronomers know the radius, mass, orbit, age of the star, amount of stellar irradiation, and perhaps the high-energy radiation environment. Then Webb or another telescope measures dayside emission. Some planets show enormous day-night contrasts and bare surfaces. Others show atmospheric heat redistribution. Some reveal carbon dioxide, some reveal sulfur-bearing gases. Some may show changing atmospheres linked to volcanism. Plot those outcomes against irradiation and planetary properties, and atmospheric loss stops being a story about one world. It becomes a measurable trend. There are hints that this population-level approach is already beginning. The 2026 Kuaꞌkua surface paper cites recent work testing whether rocky planets around M-dwarfs show trends in brightness temperature, along with studies using phase curves to distinguish atmospheric from atmosphere-free conditions. That is where one very hot planet can help researchers interpret much cooler ones. Kuaꞌkua provides an example of the nearly airless end state. If a temperate M-dwarf planet later shows clear heat redistribution, researchers can compare it with Kuaꞌkua and ask what allowed the atmosphere to survive. Was the temperate planet farther from its star during the star's violent youth? Did it begin with more volatiles? Is it more massive? Does it have stronger volcanic replenishment? Did the star quiet down sooner? Differences become information. There is also a lesson about tidal locking. For a long time, the phrase tidally locked planet was sometimes treated almost as a synonym for extreme climate, but tidal locking by itself does not decide the climate. Atmosphere and oceans matter enormously. A thick atmosphere can transport heat from permanent day to permanent night. Clouds can alter how much radiation reaches the surface. Ocean circulation can redistribute energy. A tidally locked planet with a substantial atmosphere may avoid the enormous temperature contrast seen on Kuaꞌkua. Kuaꞌkua shows us the limiting case where that redistribution machinery is largely missing. The star-facing side gets hot. The night side stays thermally faint. The fixed geometry is written clearly into the infrared phase curve. That gives climate models something concrete to reproduce. If the same models are later applied to a tidally locked planet with an atmosphere, scientists can see which differences are caused by the gas rather than the orbital geometry. Kuaꞌkua also makes us more careful with the idea of a planetary day. Around the solar system, we are used to rotation periods and orbital periods that are mostly separate. Earth turns in roughly 24 hours and orbits in a year. Mars rotates in a little more than 24 hours and orbits in 687 Earth days. Jupiter spins in about 10 hours while taking almost 12 Earth years to circle the Sun. Kuaꞌkua links rotation and orbit into an 11-hour synchronized rhythm. Its year is extremely short, but its surface does not experience an 11-hour sequence of sunrise and sunset. This matters when astronomers model climates around red dwarfs. A planet's orbital period can tell us something about its likely rotation state. Its rotation state then affects atmospheric circulation. Atmospheric circulation affects clouds. Clouds affect temperature. Temperature affects atmospheric chemistry. One measured number can influence an entire chain of planetary behaviour. The missing atmosphere then feeds back into geology. Without air or water, there is little conventional weathering. The surface remains exposed to impacts and radiation. Volcanic gases do not build up. Large temperature differences remain between hemispheres. The mantle may respond to permanent thermal forcing. Surface minerals age under direct exposure. Kuaꞌkua therefore connects stellar physics, orbital mechanics, atmospheric escape, climate, mineralogy, and internal geology in one system. That is why apparently simple planets can be valuable. At first glance, a bare rock seems easier than Earth. No ocean, no clouds, no biosphere, no complicated weather. But remove those layers, and you can see physical processes that Earth hides. Kuaꞌkua becomes a controlled case for understanding how stellar radiation interacts with rock. Then more complex planets can be built up from there. Add an atmosphere, see what changes. Add stronger volcanism, see what changes. Move the planet farther from the star, change the heat pattern, Compare an old star with a young one. Compare a 1 Earth mass planet with a 3 Earth mass planet. The universe has already run these experiments. Astronomers need to find the systems and measure the results. There is a final lesson in how Kuaꞌkwa has changed since its discovery, or rather, how our description of it has changed. The planet itself has been doing the same thing all along. In 2019, it was a newly confirmed ultra-short period world discovered through transits. Soon it became an example of a rocky planet apparently lacking a thick atmosphere. Later, work strengthened the case for tidal locking. New radial velocity measurements improved its mass and density. Then Webb obtained a spectrum of the hot surface and allowed researchers to compare the crust with basalt, olivine-rich material, fine powders, and weathered rock. The object did not become more complicated. Our measurements became better. That progression is likely to happen for many exoplanets. A point in a catalogue becomes a radius. A radius gains a mass. The orbit becomes precise. An atmosphere is detected or ruled out. A phase curve reveals heat movement. A spectrum begins revealing geology. Eventually, worlds that currently exist only as names and numbers may become physically recognizable places. Kuaꞌkwa is showing what the beginning of that process looks like. It is still distant. It is still unresolved. There are enormous gaps in what we know. We do not know its detailed topography. We do not know whether active volcanoes exist somewhere on the surface. We do not know every mineral in its crust. We do not know exactly when its atmosphere disappeared, or whether it ever possessed a thick secondary one. We do not know whether some tiny exosphere survives. We do not know what its nightside terrain looks like. Those are real limits. But look at what has already been extracted from the light. A radius of roughly 1.29 Earths, an 11-hour orbit, a very close relationship with an old red dwarf, a likely synchronous rotation, a hot star-facing hemisphere, a cold, permanent nightside with very little heat redistribution. No evidence for a substantial atmosphere, a dark, exposed surface, low silica rock, basalt and olivine-rich material among the best matches, an old surface altered by space weathering. No detected build-up of volcanic carbon dioxide or sulfur dioxide. That is a great deal to learn without ever seeing the planet as more than unresolved light. And the methods are still improving. Webb continues to observe rocky exoplanets. Laboratory spectral libraries are becoming more detailed. Models of atmosphere loss are becoming more realistic. Mass measurements are improving. Researchers are learning which wavelengths are most useful for distinguishing rock from atmosphere, and one mineral surface from another. Future observatories may be able to study cooler and smaller planets that are currently beyond the practical limits of this work. Kuaꞌkwa will then remain useful as one of the worlds where the techniques were tested under favourable conditions, not because it is typical, perhaps it is not. Its orbit is extreme, its temperature is extreme, its day-night division is extreme, but extremes make certain physics easier to see. Kuaꞌkwa shows what a rocky planet can look like after long exposure to a red dwarf, with little atmospheric protection remaining. Other worlds will show different outcomes. Those differences will tell us which parts of Kuaꞌkwa's history came from its size, which came from its star, which came from its orbit, and which came from events we have not yet identified. So a small dark planet racing around Batsu every 11 hours becomes more than an unusual destination we can imagine from Earth. It becomes a reference point. When astronomers find another rocky world beside another red dwarf, they can ask whether its heat behaves like Kuaꞌkwa's, whether its nightside stays cold, whether its atmosphere survives, whether its surface looks basaltic, whether volcanic gases appear, whether the star has stripped it bare or left something behind. Each comparison adds another piece, and as the number of measured rocky worlds grows, the old question of whether planets like Earth exist elsewhere becomes part of a much larger one. What does nature normally do when it builds a planet out of rock? Kuaꞌkwa gives us one answer: a dark surface, very little air, a permanent hot side, a permanent cold side, an old red dwarf nearby. There will be many other answers. And so our quiet journey around Kuaꞌkua comes to an end. We have followed its 11-hour year, crossed from permanent daylight into endless night, and looked at a dark, rocky surface shaped by heat, gravity, and time. Somewhere, nearly 49 light-years away, that small world is still circling Batsu, keeping one face toward its red star. If you found this voyage calming or curious, a like or subscription would be warmly appreciated. For now, let the distant planets carry on without us. Settle a little deeper, slow your thoughts, and rest well wherever you are tonight, and whenever you listen